Okay, I think it's time to start. Welcome, everybody. It's my pleasure and my privilege to open the session on gravitational lensing and shadows, which I organized together with Oleg Zubko. Today, I will chair the session. Tomorrow, Oleg will chair the session. And I remind you that we should be fairly strict about the time. So it's 20 minutes, including discussion for everybody. Yeah, so please, I ask all speakers to have an eye on the clock so that they have to be aware that I will really cut them off and go to the next talk after 20 minutes. Okay, we begin with Frederick Vancer. He's going to speak on images and photon rings of accretion disks surrounding compact objects. Please.
Thank you very much. So, okay, I'm starting to the time. Okay, thank you very much. Thank you, Oleg and Volker, for inviting me. It's a pleasure to present some recent results on this topic. So I slightly changed my topic to strong lensing for testing the nature of compact objects, because I saw that quite a lot of people are discussing alternatives to Kerr. So I was thinking maybe having this orientation would interest most people. So the work that I'm going to present is actually divided in two parts. So the first part was done in collaboration with Maciek Wielgus, Marek Abramovich, Eric Gourgouillon, Jean-Pierre Lassota, Thibaut Pomar, and Guy Perrin from Copernicus Center in Warsaw, from Harvard, and from Paris Observatory. And the second part is a recent collaboration with Sangrala, Alex Lupsaska, and Fabrice Roy, and also Maciek, who is still in that. So I will first ask the question, of course, based on the recent M87 EHT image, is it a black hole or not? So just to put some context, you all know, of course, this fantastic image of 2019 by the EHT collaboration. So together with the colleagues that I have just mentioned, we asked the question, what can we say regarding the nature of the compact object from this kind of image? So in order to try to answer this question, or at least to go a little bit further in the investigation of this question, we have considered a very, very simple accretion flow model. So it's depicted on the image here. So you have the black hole at the center, the spin axis is the vertical axis here. And the accreting material is in red. So it's very simply defined geometrically with an inner radius and an opening angle, and that's it. Then you simply have to define your density and temperature at the inner radius. You define some equipartition relation to get your magnetic field, assuming some power law for the evolution of this quantity with radius, and you have all your physical quantities analytically prescribed in your accretion flow. Then we used ray tracing simulation in the Kerr metric to compute the thermal synchrotron map from this kind of accretion flow, and we prescribed some rather usual velocity profile for the matter, like Keplerian profile, so circular time-like geodesic above the ISCO, the last stable orbit, and falling toward the object below the ISCO. So it's very simple, and I think it's important that it's very simple, because probably as of today, there is no way of having a completely realistic description of the flow. So our aim was to be as simple as possible on the plasma physics side, in order to be sure to be able to disentangle between what is due to the plasma physics and what is due to really the space-time geometry itself, which is our interest. So in the paper, I will give the reference later. In the paper, we investigated a few kinds of alternatives to Kerr, but here I will focus on only one, which is a rotating boson star. So if you don't know what this is, a boson star is a self-gravitating assembly of spin-zero boson. So you can imagine, for instance, the Higgs boson. That behaves as a single quantum body, and as such is subject to the uncertainty principle of Heisenberg. And this is actually the reason why it does not collapse to a black hole, because essentially, if you try to make it collapse, then the delta X part of the Heisenberg relation becomes smaller and smaller. This implies the delta P part to be bigger and bigger, and this acts as an effective pressure that fights against further collapse. So a boson star is a well-defined object within GR, so we are not modifying the theory of gravitation here. And I think it's a very interesting test bed space-time, not because I think that boson stars exist. I don't know, maybe they do, maybe they don't. But they are very interesting because they are extremely different from a black hole. They are well-defined and extremely different from a black hole. In particular, they have no hard surface. They have no event horizon and no central singularity. So it makes the two last properties make them very different from a black hole. So it's a good idea to try to compare the two, because hopefully if you are not able to make a difference between such a different object from a black hole, then it's probably not a very good news. And the last point on the model we use is that we did not consider boson star with photon spherical orbits, for those who know what this is, because it would lead to stability issues. So, okay, we have our accretion model. We have this with either a Kerr black hole at the center or a rotating boson star. We compute a ray-traced map of a thermal synchrotron, and we get these pictures. So the top row is a theoretical image. It's just a purely ray-traced image. And the bottom row is degraded to the 20 microarc second resolution of the EHT. So essentially, at order 0, let's say, the bottom row is what the EHT would see if you had this object on sky. The first column is a Kerr black hole. It's a standard thing. So probably this kind of image looks familiar to you. So the second column is a boson star, rotating boson star spacetime. And the third one is also a boson star spacetime, but with a different prescription for the accretion flow. Both of them are probably not very realistic. They are just ad hoc prescription of the accretion flow just to see how the image behaves, depending on the properties of the flow. And as you see, we can select some properties of the accretion flow such that the image of the boson star and the image of the black hole look very similar. And when they are degraded to the resolution of the HT, they look exactly the same. So essentially, you are not able to make a distinction between the two. So I think the important conclusion to take home is not that you cannot tell a black hole from a boson star, but what is important is that what matters here is a plasma physics. It's not GR. GR by itself is not able to provide you a very clean probe that would make you able to say this is clearly a boson star image, this is clearly a Kerr black hole image. You need to trust and to fully understand your plasma physics, because it is this plasma physics property, the properties of your accretion flow, that will lead to the difference on sky. If you want to know more, the reference to the paper is here. So, well, if you have a look at the theory image of the black hole and the boson star, you can say, oh, but there is a rather clear difference between the two. Here, there is a thin ring that you do not see here. It's the photon ring. I guess most of you know what this is. And actually, this is a transition to the next part. Can we use this very thin ring, which is a very clear distinction from the black hole and the boson star, to tell the nature of the compact object? So this is the aim, the topic of my second part. And this is actually work in progress. So here I will not show you definitive result, but I will show you the direction that we are investigating now, in collaboration with the same people as for the first project, with the great benefit of collaborating with Sam Grala and Alex Lutsaska, who are experts of these questions. So let me first remind you of the notion of photon ring. What is a photon ring surrounding a black hole? So here I have stolen a nice pedagogical image by Sam Grala in a 2019 paper, where you see null geodesics surrounding a Schwarzschild black hole. And these null geodesics are shot from a distant observer screen, far toward the right here. And they are shot towards the black hole at different impact parameters. So you see that if your null geodesic has a rather big impact parameter on the observer screen, the null geodesic will cut once and only once the equatorial plane, and will do at most half a turn around the black hole. not very interesting geodesic. More interesting geodesic is the orange one. If you are close enough, so the impact parameter is small enough, then your geodetic is able to swirl around the black hole and to do between half and one full rotation around the black hole before reaching the observer. And if you consider the very, very small set of reddish geodesic here, they are so close to the particular photon orbit that is depicted in black dashed in the panel, that they go more than one turn around the black hole before reaching the observer. And this has a direct consequence on the image plane, because so this is the theory image that we saw a few examples of this before. If you zoom on this structure, you see that there is actually not one ring, there is not one photon ring, but there is a set of subrings that you can encode by the number of half turns around the black hole. So they are called n equal 1 photon ring, n equal 2 photon ring, and if you had enough resolution, you would go to infinity. So you can divide your image, you can decompose your image, your full image here at the top. You can decompose it into various orders. N equals 0, the primary image, so photons that do at most half a turn around the black hole before reaching the observer. N equal 1 image, photons that go between half a turn and one full turn around the black hole. N equal 2 image, photons that go more than one, between 1.5 turn around the black hole before reaching the observer. And you could go further and further, but as you see, the image goes thinner and thinner. So here I have stopped at n equal 2. So you have this set of photon ring, n equal 1 photon ring, which is a little bit thicker, n equal 2 photon ring, which is extremely, extremely narrow. And as you go to infinity, as you increase the number of turns around your black hole, these set of photon rings converge to the so-called critical curve, which is a very interesting curve on the plane of the sky, because it is a pure function of the mass, the distance, the spin, and the inclination. It is completely free of any astrophysics pollution. So it would be a perfect probe of the nature of your compact object. Unfortunately, this is not directly observable because the width of this critical curve would be infinitely thin. And what you can see is the sequence of thicker ring, n equal 1, n equal 2, that are dependent, slightly depending on the astrophysics condition. So all this story of successive photon rings in black hole image was actually pointed out by essentially two papers. There are many papers now about that, but I think the two pioneering papers were the one by Michael Johnson and collaborator in 2020, and the one by Sam Gralla, Alex Lusaska, and Dan Maroney last summer. And the idea was to try to use this n equal 2 ring, the very, very thin ring here, to try to test the nature of the object, and to test if we are looking at a Kerr black hole or something else. So we are collaborating with Sam and Alex on this topic, and the idea is to try to go a little bit further than their 2020 paper. So in their 2020 paper, they arrived to the great conclusion that this n equal 2 very thin ring on sky is able to produce a universal signature in the visibility plane that is independent on astrophysics. So our idea is to try to determine does this still hold if you consider more realistic and more complex model, because in their first analysis they were considering infinitely thin, rather thin accretion disk in the equatorial plane of the black hole. So here we are considering a thick accretion disk, which is emitting synchrotron radiation, so more realistic than the initial model. And here I am showing the very first visibility curve that we obtain with this model. Just to tell you that it's work in progress, and that we are reasonably confident that the n equal 2 signature is still present when you go to a more realistic and more complex model. But this is work in progress, and hopefully you will learn more about this in the fall. So this is, of course, a quite fascinating perspective, because if you can measure this n equal 2 ring, you can ask yourself a full list of questions. So first, you can do a great consistency test of the Kerr metric, because as Sam and Alex and Dan have shown last year, there is this universal shape of the diameter of the ring as a function of polar angle on the plane of the sky. So this is a consistency test of the Kerr metric that you could perform. Next question, can you constrain the spin of the black hole? This is a subject that we are investigated with a brilliant young student of mine, Adrien Pogna. So hopefully we will be able to tell more about this also in the fall. But my understanding as of now is that, yes, you can constrain the spin with very, very good precision, but only if your n=2 ring is sufficiently ring-like, and this depends on the inclination. So there will be some good case where you can constrain your spin to exquisite precision, and some less optimistic case. And the final and most evolved question, and this will be my last word, can we constrain the nature of the object, of the compact object, by measuring this n=2 photon ring? Unfortunately, this I'm not able to report yet, because we have not yet developed simulation of the fine structure of the n=2 photon ring for non-Kerr object. But what I'm rather sure of is that this n=2 photon ring is certainly a very fascinating and interesting probe to try to constrain the nature of compact objects, and hopefully make the difference that we are not now able to make between, for instance, a Kerr black hole and a boson star, or other kind of alternatives to the Kerr black hole. Thanks very much. I am at 15:45 and I'm happy to take questions.
Thank you very much, Frederick. Yes, you're excellent in time, so we have time for questions. Other questions?
Can I ask a question?
Sure, go ahead.
So you said that you're looking at the n=2 ring for and comparing it to Kerr for more complicated objects. Do you mean boson stars, or are you looking at other objects as well? Or?
So right now we are not yet doing that, because when you want to look at the n=2 photon ring, you need crazy resolution, and this is difficult for alternatives to Kerr, because for quite a lot of alternatives to Kerr, you do not have an analytical metric. So it means terrible computing time. So for the time being, we are not doing that, but it's clearly a goal of mine to not restrict ourselves to Kerr, but have a look at the photon ring signature of alternatives and determine if we can not only make a consistency test of Kerr, but also reject some alternatives to some alternative compact object within GR, or even better, some alternative theory of gravitation.
Yep, absolutely. Yeah, thank you.
May I add to that, when you speak of non-Kerr objects or alternatives, do you think only of black holes, or also, for instance, of wormholes or other things?
No, for sure. I am also thinking of other objects, and there are plenty of talks about that, either in this session or in other sessions. So of course, it's not only black holes that are interesting, and I think that telling a black hole for a black hole is certainly something very difficult, and it's probably more easy, well, slightly easier to tell a black hole for something that is really different, like either a boson star, a wormhole, or other kind of exotic compact object.
Yeah, I think it's fairly easy to compare it with a boson star, because a boson star has no photon region, right?
Well, this depends actually, because we have taken parameters that avoid the creation of photon rings. Because if you have photon rings, it means that you have spherical photon orbits, and for boson star spacetime, when you have unstable spherical photon orbits, you also have stable photon orbit, and this is very bad for the stability of spacetime, but still it exists. So it's not that you cannot have photon rings with boson stars.
Okay, I think we have time for one more question. If you have a question, you may raise your hand, or just unmute yourself and ask the question. Are there any more questions? Apparently not. Thank you very much again, Frederick, for this talk. And we move to the next one. So this is by Ernesto Eroa. He's going to talk on shadows of black holes with a plasma environment in four-dimensional Einstein-Gauss-Bonnet gravity. Please go ahead.
Yes, I'm sharing the screen. Well, this work was done in collaboration with Javier Badia. We are both of us in Buenos Aires, Argentina. The idea of this talk is to the study of black holes in four-dimensional Einstein-Gauss-Bonnet gravity. I first present the study of photon geodesy in a plasma environment, then the black hole shadows, some observables, and finally an example taking a Shapiro plasma, and in the end, a brief discussion. Well, a novel gravity theory was recently proposed with the idea of obtaining a four-dimensional Einstein-Gauss-Bonnet theory, so bypassing the standard result that in four-dimensional Einstein-Gauss-Bonnet is purely topological and thus equivalent to general relativity. The first attempt had some problems. It was based on some particular solutions, and the complete four-dimensional field equations was not present in the first formulation. The theory was placed on firmer ground a few months after the first article by showing that in addition to the metric tensor, it propagates a scalar field, and the full action belongs to the Horndeski class of scalar tensor theories. The action was obtained by a regularization procedure in a way that is free from divergences and produce a well-behaved second-order field equations. This new theory has an emerging contribution coming from the Gauss-Bonnet term. The action is written here. The Einstein-Hilbert action is supplemented by this term, and this term contains a scalar field, and gamma is the coupling constant. This theory is free from divergences and belongs to a Horndeski class of theories with these functions. The field equations has a new term proportional to this constant gamma, and a very complicated second order function of the derivatives of the scalar field, that is this H appearing here. Another equation is obtained when varying this action with respect to the scalar field. This expression is quite long and not necessary for this talk. Well, in this theory, there is an atmospherically symmetric solution found a year ago. This solution has this form where the mass function is shown here. The parameter of the theory has units of mass squared. We consider the case where gamma is positive, so we have no problem with this square root. In the limit with gamma going to 0 correspond to the Schwarzschild geometry, and the m appearing here is the black hole mass, since in the limit when R goes to infinity, all this converges to the value of m. Well, by applying the Newman-Janis algorithm, it was found that a rotating solution of the form is possible, where the same mass function of the previous slide appears here and appears again here in the delta factor, which appears several times in the expression of the metric. A is the angular momentum per unit mass, and in the limit with gamma tends to 0, we recover the Kerr hole. The horizons are obtained from the equation delta equal to 0, and the largest positive solution of this equation corresponds to the event horizon. The idea is to study the photon geodesics in a plasma environment for this metric, and the kind of plasma is pressureless, non-magnetic, governed by this Hamiltonian. Here is inverse G is inverse metric, and omega p is the plasma electron frequency given by this equation, with A the electron charge, Ma the mass, and N the number electron density. We assume that the plasma frequency is stationary and axisymmetric, so it does not depend on the Boyer-Lindquist coordinates T and phi. As in the Kerr geometry case, in our case also this inequality is a necessary and sufficient condition for a light ray with frequency omega 0 to exist at a given spacetime point. Omega 0 is the frequency of the photon, and omega p is given here is the plasma electron frequency. The idea is to write down the Hamilton-Jacobi equation for photons that which has this form, and we introduce these ansatz in order to separate the equation. Substituting these ansatz into the Hamilton-Jacobi equation, we arrive to this expression where the primes correspond to R derivative here and to theta derivative in this term. So we can take in this long expression, we can take the terms dependent on R and the terms dependent only on theta, and then with the idea to separate variables. But for doing so, we need also to separate this term. So we choose a plasma frequency that can be separated into an R part and a theta part with these, in principle, arbitrary functions, but then we will take some functions that are physically interesting. By substituting this expression into the Hamilton-Jacobi equation, we can separate it in the form that's shown here. The left side of the equation is only a function of theta, and the right-hand side only a function of R. And so in this case, we have that we have separated the variables. So this the right-hand side had to be a constant value, and the left-hand side and the right-hand side should be the same constant value, K. Well, we can choose K as a separation constant, or we can use another one that's very similar with the two other constants of motion, P phi and the omega 0. We will use Q instead of K for the separation. And so after the separation of the equation, using the Hamilton equation, in the usual way, we can separate the equations into 4 ordinary differential equation, one per coordinate of this spacetime. Here we have defined some standard functions to write down this expression in an easy, a better form. So the air function, that is very important, is given by this equation, and the theta, capital theta function is given by this one. Finally, there is another auxiliary function that is P, given here. So we have four ordinary equations in order to study the geodesic motion of photons in the presence of plasma. Well, in order to obtain the shadow, the idea is to study the spherical photon orbits that fulfill the condition that the function R and the derivative of this function capital R equal to 0. Such solutions are stable, satisfying the second derivative is positive. From the equation R equal to 0, we obtain this equation, and then replacing in the derivative, we have that, which is a quadratic equation for P phi with this solution. In order to obtain Q in terms of this R, in terms of the solution shown in the previous slide, a helpful intermediate step is this relationship, and putting all together after some algebra that is not very difficult, but rather cumbersome to vision here, we have that Q is given by this expression in terms of R. And so we have found the critical values of P phi and Q associated with the spherical orbit. Any trajectory you should have that theta, capital theta, should be positive or 0 because of the square root that appears on the theta equation. There is a square root over capital theta, so it has to be positive or 0. This condition is translated to this expression, and this equation defines the photon region. Spherical photon orbits exceeds at values for R and theta for which this inequality is satisfied. The idea is to study the shadow for a distant observer, so it's the set of points that never reach infinity and instead cross the event horizon in the sky of this distant observer. The boundary of the shadow consists of those rays that asymptotically approach the spherical photon orbits of the spacetime we are studying. In order to relate the directions in the sky with the constant of motion, we take an observer at theta equal theta of the observer in the asymptotically flat region and construct this orthonormal tetrad. And we use the standard, or rather standard, celestial coordinates, and the contour of the black hole is described by a parametric curve as usual, in these cases. We define three observables: the area of the shadow, its blackness, and the horizontal displacement of the centroid. The area is calculated like that. The factor 2 erasing that the figure is symmetric. The shadow is symmetric, has an up-down symmetry. The blackness is related to the deformation, and the horizontal coordinate of the centroid is given here. with the same factor 2 as in the definition of the area. Well, to give an example, we use a Shapiro plasma, which is a well-known case of dust that is at rest at infinity. In the curved spacetime, the mass density and the square plasma frequency go as R over minus 3/2, being independent of theta to a very good approximation. However, such distribution cannot put in a separable form, so we take the frequency and having an additional frequency dependency as it was done in this paper before. So the plasma frequency has this form that slightly depends on theta by this term, this factor that appears here. So it has a strong dependence on R and a slight dependence of theta. Omega C is a constant dependent of the particular model adopted in a particular case. At large distances, the metric approaches the curve 1, so we expect that the Shapiro solution is still valid in our model, that the black hole is not a curved black hole. At the small distances, the metric may be quite different from the curve 1, so we work on the assumption that the plasma density is not significantly affected, so we can use this model. This is an assumption. Well, we show here some contours for different values of the dimensionalized parameter of the theory, gamma over square m. And these are the values of each column. And here, the different values of the square plasma frequency, or the square omega c is the constant in the plasma frequency, divided by the photon frequency. We take here several values. The spin of the black hole is taken in this plot as being adimensionalized with the mass 0.9, and it should surrounded by the Shapiro plasma shown here from an equatorial observer. In this case, the condition gamma over m squared should be less than this value. This is necessary for the existence of the event horizon of the solution. If gamma over m squared is larger than this value, we have a naked singularity, and the idea is to study a black hole, not a naked singularity. The trajectory of photons with frequency omega 0 depend only this ratio. Well, here are plot the observables. They are well defined before. In the top row are shown as functions of the frequency, the ratio of frequencies, and in the bottom are shown as functions of the parameter of the theory. The main feature of this plot, for a given value of the plasma frequency omega c, we can see that for fixed parameter of the theory, the shadow reduces in size, is less deformed, and has a smaller central displacement as the photon frequency decreases. In particular, the shadow disappears entirely below a certain photon frequency due to the appearance of the forbidden region. This forbidden region starts as two cap around the poles and grows towards the equatorial plane as the frequency decreases, leading to a reduction of the shadow size. This is a consequence of of the presence of the plasma. For a fixed photon frequency omega 0, the shadow is slightly reduced in size, is less deformed, and the central displacement slightly grows as gamma over m squared increases. The effect of increasing the parameter gamma is more prominent for high frequency photons, particularly in the case of lightness. To finish, we have studied how the presence of plasma modifies the shadow corresponding to rotating black holes in the novel four-dimensional Einstein-Gauss theory, assuming that plasma obeys the separability condition. We have obtained the expression for the celestial coordinates of the shadow contour as viewed by a faraway observer. We have presented three observables: the area, the blackness, and the center of the shadow. And the work presented here is a particular case of the shadow cast by a class of rotating black holes surrounded by plasma, which result from applying the Newman-Janis algorithm to spherically symmetric spacetime, determined by a mass function satisfying that R goes to the capital mass M when R turns to infinity. That we have recently put on archive this article. So the idea is you can replace the Gauss-Bonnet M, the mass function M, with another mass function with the only condition that the limits goes to the mass of the black hole, and do the same and obtain some general expressions that can be applied to any black hole with this form. Thank you very much.
Okay, thank you very much, Ernesto. I'm afraid that we have no time for discussion. I'm very sorry, but I think we have to move on. Thank you very much again for your talk, but I think we have to move on. So we have now two talks from colleagues from Portugal, from Carlos Herdeiros group. The first one is Sergio Xavier. He's going to speak on comparing Kerr-Sen and Kerr-Newman black hole shadows. Ernesto, would you please stop sharing so that Sergio can share his screen? Yes, okay, thank you.
Okay.
Okay, looks good, yes.
Okay, so let me start. First of all, thank you for the introduction and for the opportunity. And today I will talk about the comparison between shadows from shadows of black holes from two different theories of gravity. And this work was done in collaboration with Pedro Cunha and Carlos Herdeiro from Portugal, and Luis Crispino, that is my advisor. And okay, so here's the outline of my talk, where in the first part I will try to motivate you to the problem and introduce the space-time that we will be analyzing. And after that, we will discuss about the black hole shadows of these space-times and how we can use the observer to compare between these shadows. Okay, so as all you know, the general relativity theory, the GR theory described by Equation 1, has passed by numerous experimental tests with flying colors. But the majority of this test was performed on the weak field regime. So it is expected that in some scale, GR will break down, or at least will be modified, in particular in quantum regime. In this respect, black holes become a natural configuration to explore the quantum nature of gravitational fields. And in fact, we are now living a time where tests on strong fields become more and more recurrent. One example of this test was the discovery of gravitational wave by LIGO in 2015. And it is believed that this wave was producing the merger of a binary of black holes with several solar masses. And another important evidence of this compact object was obtained a few years ago. So the Event Horizon Telescope collaboration released the first image of the compact object that lives in the Messier 87 galaxy. Therefore, gravitational waves in black hole shadows opened a new window to us to help us in the understanding of the universe, and we can use them as a tool to test alternative theories of gravity. In this sense, we are analyzing this work, the shadows of black holes, from two different theories of gravity. One black hole solution that comes from GR theory, and another black hole solution that came from the low energy limit of periodic string theory. And more details about this work can be found on this paper here. And now let's move on to the space-time. And in fact, we can discuss about why study charged black hole, because we know some mechanisms to discharge astrophysical black hole. But nonetheless, it still has some reason to do that. So besides the theoretical aspects of the problem, there are recent papers like this one by Zhang that shows that some astrophysical phenomena like some gamma ray burst events can be explained if we consider the merge of charged black hole. Okay, so the first spacetime that we will be dealing with is the well-known Newman solution. That is a solution from GR field equation that describes the spacetime of a charged and rotating black hole, and whose line element reading Borel-Lindquist coordinate is given by equation 2. And here, M is the mass of the black hole, Q is electric charge, and A is the spin parameter, the angular momentum per unit mass. And we shall compare the Newman solution with the Constrain spacetime. That is a black hole solution that comes from the low energy limit of theoretic string theory. And it also describes a charged and rotating black hole, and here M, Q, and A has the same meaning as I told you before. And now we are looking for the domain of existence of black holes in both space-time. So the green region in this plot shows the values of the angular momentum in electric charge that allows the existence of a black hole in each space-time. And you can see from this plot that the Constrain solution allows a wide range of electric charge. One important idea that we must keep in mind is the fact that generally, when you compute the mass and the angular momentum of a black hole at the event horizon, this value will have or will be equivalent to these values calculated at infinity. But for another class of space-time that has some part of the energy stored outside the event horizon, this, as the case of Newman and Constrain, this will not be true. So following this work of Delgado and Radial, we can write the mass and the angular momentum computed at the event horizon as function of the mass, the charge, and the angular momentum computed at infinity. And for Newman spacetime, these are the results. And here are the expression for Constrain spacetime. And so keep in mind that idea because it will have a major role in the interpretation of final results. And now let's discuss about the black hole shadows. And in fact, the study of the shadows is a very old one, dating back to the 70s, where one of the seminal paper on this topic was due to James Maxwell Bardeen, where he calculated the shadow of an extremely Kerr black hole, obtaining this famous D-shaped form for the shadow of a rotating black hole. And indeed, if you do a quick search on arXiv, you can see that the area of black hole research is a growing area, in particular in the recent years. Okay, but to study a shadow of a black hole, we must understand how light trajectories behave in the vicinity of this compact object. So basically, what you need to do is analyze the geodesic equation for new particle, which for Newman spacetime are given by this set of equation here, and for Constrain spacetime are given by this set of equation in this box, where in both cases, E represents the total energy of the photon, L is azimuthal angular momentum, and Q is a constant like a Carter constant for carriage spacetime that is associated with latitudinal motion. And okay, so the boundary of the shadow of a black hole is associated with a class of orbits that are called fundamental photon orbits. And for the class of spacetime that we are doing this work, they are characterized by having a constant radial Borel-Lindquist coordinate, and then they are doubled as a spherical photon orbit. And to help us in the understanding of these spherical photon orbits, we can introduce these two parameters, where you can see that the phi parameter is associated with the azimuthal angular momentum of the photon, and the eta parameter is related with latitudinal motion. So always that the eta parameter is equal to 0, it means that we are dealing with equatorial motion, okay? And as already said, the condition for the existence of spherical photon orbit are given by these two expressions here. And from now on, in order to compare the motion of light in both spacetime, we use the perimeter radius as defined by equation 29. And now we can plot the parameter of the spherical photon orbit for trajectories in both spacetime as function of the perimeter radius. So the solid line here shows the value of the parameters of spherical photon orbit for trajectories in Cartesian spacetime, and the dashed line shows these values for Kerr-Newman spacetime. And remember that I told you that always that eta parameter is equal to 0, and you can see in this plot that this happens for both spacetime in two regions, one closer to the event horizon and another more distant. So always that eta parameter is equal to 0, we are dealing with equatorial motion. In this case, equatorial circular motion. And basically the difference between these two equatorial orbits are the signing of the phi parameter in each region. So for the orbit closer to the event horizon, you have a positive phi parameter, which means that this orbit co-rotate 1 with the spin of the black hole. Whereas for the another equatorial orbit, you have a negative value of the phi parameter, which means that this orbit is a counter-rotate 1. So the main message of this image is that the equatorial circular orbits for Cartesian black hole always happen with a larger perimeter radius than the same orbits for Kerr-Newman. And this gives us some insight about the spectral behavior of the shadow. Okay, so here is an example of one of these spherical photon orbits. It's a co-rotate one. In blue, you see the trajectory for Cartesian black hole. In red for Kerr-Newman. Here is another example of a counter-rotating spherical photon orbit. And now we can introduce the coordinates of the black hole shadow edge in the image plane of a distant observer, as given by these two expressions here. And you can see that these coordinates are related with the parameters of the spherical photon orbits. And now we are plotting the shadow of these black holes as seen by a distance observer at the equatorial plane. So in red, you see the shadow of Cartesian black hole, and in blue, the shadow of Kerr-Newman. And you can see that although these two shadows are very similar, the difference between these two shadows is very small, it increases as you increase the value of the electric charge. And in order to analyze this difference, we will use an observable defined on this paper here by Hioki and Maeda that is called the shadow radius, that can be basically defined as the radius of a circle that intercepted the shadow in three positions: the top position, the bottom position, and in this position here, related with that counter-rotating equatorial orbit. And you can write the shadow radius as function of the black hole shadow edge coordinates. And now we are plotting the shadow radius as function of the electric charge. So in red, you see the results for Cartesian black hole, in blue for Kerr-Newman. And you see that for highest value of electric charge, the size of the shadow decreases, although the difference between these two spacetime remains very small. And in order to quantify this difference, we introduce the relative radius difference as defined by equation 33. And now we plot the relative radius difference as function of the electric charge for different values of the angular momentum. So the green line shows the result for the smallest spin of the black hole, and the blue line shows for the highest one. And what we can learn from this plot is that the relative radius difference increases with the value of the electric charge, but decrease as you increase the value of the spin of the black hole. But in all cases, the shadow of Cartesian black hole is always larger than the shadow of Kerr-Newman. And we try to provide explanation for this behavior using the fact that for a Kerr black hole, as you increase the value of the angular momentum of the black hole in general, the size of the shadow radius decrease. And so, but for Kerr black hole, the angular momentum calculated at event horizon is equal to the angular momentum calculated at infinity, which is not the case for the black hole solution treating this work. So what we thought was, with the black hole, Kerr-Newman or Cartesian has more angular momentum at event horizon, because that black hole that has more angular momentum at event horizon will have, consequently, or we can expect, we have a smaller shadow. And when we are analyzing this property, what we obtain is this plot here showing that the Newman black hole always has more angular momentum. Okay, to conclude, I show in this seminar the shadow of black holes from two different tiers of black hole solution from two different tiers of gravity. And we see that the black holes, the shadow of the black hole that comes from the low energy limit of theoretic string theory always has a larger shadow than the black hole from GR theory. And we try to provide explanation for this behavior based on the fact of quantities computed at event horizon compared with this quantity at infinity. And we know that due to the electric charge, the black hole solution treating this work are not accurate model for astrophysical black hole. But this can be seen as a first step to study more realistic scenario. So here's my acknowledgement and thanks for your attention.
Okay, thank you very much for this talk. We are now very good in time, and there's already a question by Luis Crispino.
So hello, everybody. It's not a question. I am Sérgio Xavier, supervisor. I'd just like to mention that Sérgio is not from University of Aveiro in Portugal,
Yes.
but from
Oh,
University
sorry,
of Pará
sorry.
in Brazil, Amazonia. Thank you very much, Boca. Good work, Sérgio. Well done.
Okay. Thank you.
My apologies. Yeah. Okay, Alexander also has a comment or a question. I don't know.
Yes, yeah, I have a question or a remark. I don't know. When you showed Hioki Maeda picture, could you show it again?
Yes.
13.
Here.
No, previous one. Previous one. When you show shadows
Okay.
and deformation of shadow. This one.
This.
So actually, in 2005, we showed that there is a maximum value of impact parameter in the vertical direction. It depends on spin as 2a value. And Hioki and Maeda used our paper, but they didn't pay attention on this, in principle, direct opportunity to measure spin if people could reconstruct shadow for equatorial plane. Because there is a value of, let us say, maximal impact parameter in vertical direction is the same for any spin, is theorem. But dependence of this position is 2a. So that is very, I think, important feature of these shadows for equatorial plane for Kerr metric. So, but also, you see, I have a question about opportunity to evaluate, let us say, charge, or in your consideration from recent observational data from Event Horizon Telescope, because there is a limit for size of shadow. In this case, roughly speaking, charge is responsible for size of shadow. In this case, you also could evaluate charge. If you pick up, let us say, constraint from Event Horizon Telescope data, they published article on this issue, I think, months ago.
Yes.
Thank you.
So I don't understood. I don't know if I understood correctly, but I mean, I understood your general comment, but I'm not sure if you.
No. I just because I think it's very important. I would like to repeat.
Okay.
So this size is square root of 27 in M units, maximal value. It's independent on spin. It's very important property of shadow for equatorial plane. And dependence on spin of this position for maximal impact parameter 2a. So if people could reconstruct shadow for equatorial plane, immediately you could evaluate spin without, let us, analysis of, let us say, oblateness and other things. That is my remark. Do you understand?
Oh yes, I think.
Because also when you showed, and also one remark, previous slides, when you showed some pictures about, let us say, dependence of, let us say, radial velocity, it looks like almost, let us say, figures from Chandrasekhar book, but you cut it this.
Okay, I see.
Yes, do you understand? In Chandrasekhar, it was eta parameter is a function of radial coordinate.
Yes.
No, not that only this, but so you cut it. Do you understand? When dependence on radial coordinate. Critical parameters is dependence on radial coordinate.
Oh, I
Okay.
see. You,
Okay.
yes.
Yeah.
In this case, okay,
Actually,
sorry, too late.
excuse me. Actually, Bardeen, Chandrasekhar had taken this from Bardeen, right? It's already in the
Yes.
Bardeen paper.
Yes. The Chandrasekhar uses the same method for Bardeen.
Yes, yes.
Yes.
No, okay, but it was remark about another picture, but it's no matter. I think it's not very important. I could send you references later. Okay, thank you.
Okay, thanks for these comments, Alexander. Last question by Torben.
Yeah, can you hear me?
Yes.
Okay, I have a question. Did you ever consider doing lensing in the Carriage metric with solving the equations of motions with elliptic integrals and elliptic functions? From what I saw, it should be possible.
Okay, so in this work we don't analyze this problem, and in fact this one is one of the future perspectives to study this problem in particular that you mentioned.
Yeah, I think it has not been done. I'm not aware of anybody having written the solution in the Carriage metric really in terms of elliptic integrals. Although it should be possible. Yeah, it's just a polynomial of not higher than fourth order, so it should be possible, yes.
Yeah, I mean, it's very analogous to the Carriage metric.
Yes.
But it seems to be.
Yeah, it's very similar to the Carriage metric.
Thank you.
Okay, I think we should move on. Thank you very much again, Sergio. And our next speaker is Haroldo Lima Jr.
Yes.
Is he there? Yes, okay, good. Yes, yes. So please share your screen. And the title is, Can Different Black Holes Cast the Same Shadow?
So can you see now my screen?
Yes.
And the pointer is working?
Yes.
Okay.
You're not in full screen yet, Haroldo.
Is it now?
Now it's okay. Okay,
Okay.
please go.
So, hello everyone. My name is Haroldo Lima Jr. I'm from Federal University of Pará in Brazil, and I'm going to present this work, Can Different Black Holes Cast the Same Shadow, which was done in collaboration with Pedro Cunha and Carlos Herdeiro from University of Aveiro, and my advisor, Professor Luis Crispino. You can see more details of this work in this archive here or in this physical review D. So the strong gravitational field regime has been tested in the recent years. For instance, we have the gravitational wave results. And for our interest right now, we have the HT results, the results for the shadow of a black hole. So there are many interesting theoretical questions to be answered right now with this result. One of these questions is the question for the degeneracy of the shadow. So it is basically to answer under which condition two different black holes can cast exactly the same shadow. So first, let's review very quickly the Schwarzschild solution and the Schwarzschild shadow. So the Schwarzschild solution is described by this line element here. We can obtain the geodesic motion, the no geodesic motion from this Lagrangian. So we can restrict to our results to the equatorial plane. And we have also these two conservative quantities here, which are the angular momentum of the photon and the energy of the photon. So this allows us to write a radial equation of motion as given by this. So where this V here is a potential, which is given by this expression here. So in this case, the light rings, which are related to the boundary of the shadow, are determined by these two conditions here. So it's basically the point where the R dot is equals to 0 and R dot is equals to 0. which are the conditions for the light ring, and the shadow is related to the critical impact parameter of such light rings. We can translate these two conditions here to the function v, to the potential v. So it's basically a maximum of this function. So for the Schwarzschild black hole, the light ring radius is at 3m, and the critical impact parameter associated to the light ring, which is this size of the radius of the shadow as seen by an observer at infinity, is equals to 3 square root of 3m. So this potential V has the disadvantage of depending on the constants of motion, for instance, E and J. So we can define a new effective potential, which I call here H, by factorizing all these constants, the dependence on these two constants. So we arrive at this function H, which is the square root of this term here divided by R. And note that the light rings are now determined by the points where this function H is equals to 1 over the critical impact parameter, and its derivative is equals to 0. So here I show the plot of this function H in terms of R. So it has a maximum value here, which is associated to the light ring. We can write the relation between the impact parameter, the critical impact parameter associated to the shadow edge, and the observation angle, beta here, associated to a static observer, by this following relation here, where R OBS is the radius of the observer. So we know it's very known that the shadow of the Schwarzschild solution is a circular ring, and it has this shape here. The carriage geometry is a little bit more complicated. This is the line element of the carriage geometry, where sigma and delta are these two functions here. And the event horizons are located at the points where this delta is equals to 0. So R plus here is the event horizon, R minus the Cauchy horizon. And since the carriage geometry is not spherical symmetric, one cannot restrict the geodesic motion to equatorial plane without loss of generality. But fortunately, there is a hidden symmetry in the carriage spacetime, so we can write the first order equations of motion. And this hidden symmetry is encoded in this Q here, which is known as the Carter constant. So we can write the radial and the theta equations of motion in this way here, in a very simple way, where R is a function of R and theta is a function of theta only. And now the edge of the shadow are determined by the set of spherical photon orbits. And the set of spherical photon orbits are the points where R is equal to 0 and its derivative is equal to 0. So by using these conditions for the spherical photon orbits, we can obtain the shadow of the Kerr black hole in terms of the spin parameter. Now that we have reviewed these properties of Schwarzschild and Kerr, we arise this following question: can the shadow of different black holes be exactly the same as the Schwarzschild or the Kerr one? So first, let's deal with the static case. So we consider a spherically symmetric, asymptotically flat, static black hole spacetime described by this lining element here, where V is a function present in the Schwarzschild metric. So this 2m here fix the event horizon coordinate. So we are dealing with black hole geometries, and A and B are general functions. So the equations of motions for the radial coordinate they are given by this expression here, where now this V is a little bit different. So we define this effective potential H, which is the square root of A times V divided by R. And the light rings, as we have seen before, they are determined by the points where this H function is equals to 1 over lambda, and its derivative is equals to 0. Again, the relation between the impact parameter and the observation angle is given by as this expression here. So the degeneracy condition happens when two observers at the same radial position, R OBS, in the Schwarzschild and in the generic spacetime, sees the same observational angle, beta C, associated to the shadow. So from this relation here between the critical impact parameter and the observation angle, we find that the light ring in the generic geometry must satisfy this condition here. So it must be equals to the Schwarzschild impact parameter divided by the square root of this function A present in the generic spacetime, computed at the observer position. So we can compute the light rings for the light ring properties for this spherically symmetric spacetime. So the light ring is determined by this condition here, and the radial position, the critical impact parameter, sorry, and the coordinates of the light ring is determined by this second expression here. So the notorious feature is that regardless of the function B, if A is equals to 1, then the shadow will be exactly the same as the Schwarzschild one, since this term here depends on this derivative. So A must be equals to a constant in general, but we can always choose equals to 1. So in this case, the light ring, we have a radial coordinate equals to 3m, and the critical impact parameter will be exactly the same as the Schwarzschild one. So we conclude that any metric with this profile here, so which has this general function B of R here, is shadow degenerated with respect to the Schwarzschild solution. And this is a sufficient condition for shadow degeneracy, which we have called in the paper class 1 of shadow degenerated spacetime. Now, what happens if A of R is different than 1? Can we have a shadow degenerate in this case? Well, the answer is yes. We call this class 2 of shadow degenerated spacetime, and we note the following properties. So since the GTT is less than 0 outside the event horizon, this condition here must be satisfied. So 1 over the impact parameter must be greater or equals to this effective potential H. And the radial motion can only be inverted if this inequality here is translated into a equality, and this function H vanishes at the horizon. So if we remember the condition for the shadow degeneracy in the generic case, and we use this property here, and we use this inequality, we have a necessary and sufficient condition for the shadow degeneracy. This can be translated into this constraint on the function A of R. So the function A of R must be less or equal to this function here, this R function here, where R OBS as before is the function A computed at the observer position. And this inequality here must be equal to equality at least once outside the event horizon. At least once, and this will coincide with the radius of the light ring. So now in this is the class 2 shadow degenerate spacetime. So now we present some examples. An example of the class 1 spacetime is the Simpson-Visser metric, which is a metric proposed as a minimal modification of the Schwarzschild one. If we introduce these radial coordinates R here, we have this following line elements where we have the same a similar and spacetime similar to the Schwarzschild one, but we have this additional function here. And this is an example of the class 1 shadow degenerated spacetime. Here we show the Schwarzschild, the lensing, the gravitational lensing and shadow for the Schwarzschild black hole and for the Simpson-Visser black hole. The shadow are the same as expected, and there is a subtle difference in the gravitational lensing. For the class 2 example, we constructed this function A of R here in our paper as a concrete example of this shadow degeneracy phenomena. So this function A of R we constructed is given as this expression here. So it's depends on 1 over R squared and 1 over R to the 4. And we have some coefficients here. So this depend on the light ring position, and we have these coefficients here. U is the ratio between the coordinate of the light ring and the coordinate of the observer. So if the observer is located at infinity, this U is equal to 0, and this function is very simple to write. And here we show the H function for different values of the light ring position. So now we have chosen here three values of the light ring position. As we can see, the shadow is always, the central shadow is always the same, but in this case, the gravitational lensing can be quite different. Once that we have established the degeneracy results for the static case, it's natural to ask if generically rotating black holes can also be shadow degenerated with the Kerr solution. So we assume here that the generically rotated black hole admits separability of the Hamilton-Jacob equation. Otherwise, it would be very hard to solve the problem in a numerical way. So Bennett and Francavilla have shown that the most generic metric that admits separability of the Hamilton-Jacob equation is written in this way here. So it depends on several functions, A's and B's, where the A functions, they depend only on the radial coordinates, and the B functions, they depend only on the theta coordinates. The equations of motion for these generic rotating black holes admitting separability are written as these two expressions here. So there is a dependence on the A functions here, and there is a dependence on the B function here. So we note that if A2, A3, A5, and B2 is equals to 1, the spherical photon orbits, which determines the edge of the shadow, will coincide with the Kerr1, regardless of A1, B1, and A4. So this gives us a clue that the degeneracy problem for the rotating case is related to this constraint here on these three A functions and this B2 function. So since the shadow edge as seen by a faraway observer is determined by these two conditions here, so we have this coordinate X and this coordinate Y, and if A2, A3, A5, and B2 are equal to 1, this will result in the same shadow as Kerr. So this condition here is a sufficient condition for shadow degeneracy for the rotating black hole case. Thus, any black hole with this form here, with the dependence on the remaining functions, is shadow degenerated with respect to the Kerr solution. So now we show some examples. One example of shadow degeneracy is the rotating Simpson-Visser spacetime, which is constructed by applying the Neumann-James algorithm to the static case that we have seen before. So we note that the resulting solution is similar to Kerr, but we have this term here, which is the term present in the Simpson-Visser metric, and the rest is equal to the Kerr metric. So here I show the edge of the shadow for the Kerr solution and for two parameters present in the Simpson-Visser solution. As we can see here, the shadow is always the same. Here I show the shadow and gravitational lensing obtained by performing ray tracing techniques. So again, the shadow is the same, and there is a subtle difference in the gravitational lensing very close to the shadow edge. Perhaps a more interesting result are black holes with non-Z2 isometry. That is, black holes that the south and the north hemisphere are not equal to each other. So there is a difference between the north hemisphere and the south hemisphere. So we constructed this type of metric in this paper. So it has this form here where the Z2 isometry breaking term is given by this B1 here. In particular, this cosine and cosine to the 3 terms here, they break this Z2 isometry. So here we have the event horizon geometry for the CAS solution. The north hemisphere is equal to the south hemisphere. Here we have a non-Z2 isometric solution. So you can notice that the north hemisphere is different than the south hemisphere. And here it's the same. So the event horizon geometry can be quite distinctive from the CARE1. Despite that, the shadow edge is always the same, regardless of these parameters present here in the metric, these alpha parameters here present in the metric, which is a very intriguing result. So to conclude, around black holes, light ring can be bent an arbitrarily large angle, and this makes possible to black holes cast a shadow, which is the visual appearance of the black hole. And the black hole are, the shadow of the black hole are usually taken to be the Schwarzschild, the K1. And as we have shown here, there exists a class of black hole solutions that can cast exactly the same shadow as the Schwarzschild or the Kerr black hole 1. And we have obtained what types of constraints you need to put in a generic metric to obtain this result. So shadow, we haven't used any type of field equation. So shadow degeneracy results holds for gravitational theories beyond general relativity. So it's possible to have an alternative theory of gravity that the solution is different, but the shadow, the black hole shadow, will be exactly the same as the vacuum solutions of general relativity. So this is the end of my presentation. I will be very happy to answer any question if there is.
Okay, thank you very much, Aroldo. I think we have time for one question. Daniel.
Yes, thanks. I have a question about the geometry of the horizon in this Z2 breaking black hole. Is that a real geometric feature that the horizon is now not Z2 symmetric, or is it just a sort of a coordinate feature, a feature of the coordinates that you're using? I mean, I ask because the shadow itself is going to be equatorial symmetric, as you mentioned, and so I wonder is the horizon itself really not a sphere anymore, or not a ellipse anymore, or?
Yes, the horizon is not Z2 symmetric anymore. This is the geometry of the event horizon, and that's this result was very intriguing for us when we were studying this problem, because the event horizon geometry can be very assume a very unusual shape. For instance, this last shape here, but the shadow is always symmetric, is always equal to the K1.
But when you are plotting the horizon, what are you plotting? Is this a coordinate picture, or is this an isometric embedding?
It's an isometric embedding.
Okay. Thank you. I think that was yeah.
Yes, thank you.
Okay, good. Yeah, thank you very much again for your talk. Sorry. And we move on now. Our next speaker is Daniel, who was just asking the question. He is talking on fastball shadows. I can read my own handwriting. Emergent horizons from microstructures.
Yeah.
Please go ahead.
Okay, thank you. Yes, so I'm going to talk a little bit about fuzzball shadows, which is mainly based on this work here that I cite here with with collaborators that include string theorists like myself, and also people who are involved with EHT and ray tracing. And so I'm going to be talking a little bit about fuzzballs in general, and so I invite you also to this review about how these objects can be important for observational studies. Okay, so I'm going to talk a little bit about, since I don't assume that that everybody is familiar with fuzzballs, so I'm going to introduce this concept and try to tell you what they are and why we should be interested in them. Before going on to the actual computations and images of these fuzzballs, and to talk about how these fuzzballs can have emerging horizons and how they might be interesting for observability studies. Okay, so let me just introduce fuzzballs in just a very brief, very briefly, right? So fuzzballs is a concept or a paradigm in string theory. And so how does this come about? So in GR, we have black holes, right? It's very familiar to us. And in quantum gravity, we expect something to happen to this black hole. Something must replace it, or something must resolve it, or solve the problems of the black hole. Okay, and so you might think that, all we really need of quantum gravity is to solve the problems around the singularity, because that's where curvature gets big. But there are arguments that show that you also need corrections, large corrections at horizon scales as well. Okay, and the main example of this is the information paradox, where information is trapped inside the black hole from formation or a merger, anything that you throw into the black hole, right? The information of what you have thrown into it gets trapped in there. The only thing that can come out of the black hole is Hawking radiation, semi-classically, right? Quantum mechanically. This Hawking radiation is thermal, so it carries absolutely no information about the stuff that was in the black hole or the stuff that formed the black hole. Because it carries absolutely no information, the information paradox, in sort of a rough sense, is the question: what happens to this information that is trapped inside the black hole? Okay, now the most obvious counter argument to this is to say that, well, Hawking's calculation is a semi-classical calculation, and so in particular, when you do this more carefully, there will be small quantum corrections to this to this radiation, and so maybe it's not really exactly thermal, and it carries some information. That's of course a possibility. But the rather surprising result or theorem by Mathur a number of years ago is that such small corrections, so small quantum corrections at the horizon to Hawking radiation, cannot be enough to recover the information that's trapped inside the black hole. This is a very crucial result that leads to the assumption or the realization that in a theory of quantum gravity, you really need something that has new physics at the horizon scale, right? Not just at the singularity where you thought the singularity was, but you need large corrections at the horizon scale. And so this is in a nutshell the idea behind the fuzzball paradigm. Okay, so fuzzballs it's a funny name, but the idea is really that you replace the black hole entirely by an object called a fuzzball, which is sort of a ball of stringy quantum fuzz, right? Structure, microstructure, that extends all the way to the horizon scale. Okay, and this is supported by stringy mechanisms from collapse. Okay, so this is sort of in a nutshell the idea of the fuzzball paradigm. Now, why do we care about this? Well, I like to take the viewpoint of we're in a very exciting era of gravitational phenomenology, gravitational waves, and black hole imaging, and typically what people study are exotic compact objects that are motivated or constructed from a bottom-up approach, right? Things like boson stars, wormholes, gravastars, etc. And some of these have problems with consistency or parameter range. Some of them, it's not really clear how to embed most or all of them into a theory of quantum gravity, right? We don't really know how to get this from a top-down approach. And so I just want to mention this, not to be disparaging towards other models, because I think they're very useful, very interesting, but just sort of contrast this with the idea of fuzzballs, which are really top-down models, top-down objects that have a very good embedding because they come from a theory of quantum gravity, namely string theory. Okay, and so these are objects that replace the black hole, resolve the black hole, replace it by an object without a horizon. And so we have horizon scale microstructure of which we can write down explicit solutions, right? And I think this is very interesting because it sort of begs the question, can we study these in an observational way? Can we find observable signals from these fuzzballs, right? Can we distinguish them from black holes in observations? And so that's sort of the big picture context of this fuzzball idea. Now let me talk about the actual images of fuzzball, right? And so since I told you that these fuzzball objects don't have a horizon, but in string theory we expect them to replace the black hole entirely, then we sort of need to understand how these fuzzballs can achieve a blackness, right? They don't have a horizon, so geodesics or light rays will not get trapped in them. But nevertheless, we expect them to be somehow black, effectively black. And so that's the first question that I'm going to answer on the next slide. And then the second question is sort of the next order question, if you will, right? Like, okay, so they are effectively black, so they mimic a black hole very well, but can we still distinguish them somehow? And so my setup is, so these fuzzballs are unfortunately rather complicated geometries, right? So I'm not going to give you the details of the geometry. You're welcome to look in the various papers that I cited already. The setup is we're going to look at these geometries called multi-centered geometries. Now, again, the details are not very important, but the setup that you should sort of have in mind, the structure of the geometry is that there are different sources in different locations in space. And in particular, we're going to take a particular geometry, a particular structure of sources where we have 2 point sources on the z-axis, and we have one ring source that's in the equatorial plane. Okay. So that's sort of the structure that you'll also be able to see in the image in just a second. And so I guess I don't need to introduce this to this crowd, but we're going to image these using a 4-color screen where the 4 quadrants of the sphere at infinity or at a very large radius are colored in 4 different colors, and we place the camera in this white dot here in one of the corners. And of course, the object is in the center. Okay, so let me show you the actual images of such a fuzzball, right? Of such fuzzballs. So here we have a bunch of images, and so I'll go through some of these images in some detail, right? So the first row is exactly the 4-color screen, right, that I was just talking about. And in the columns, I've always imaged a different geometry, right? And so in particular, you should notice that there's this parameter lambda, and a parameter lambda, this is called a scaling parameter. Now, it's not very important how this comes about or what it really represents. The most important thing to remember about this scaling parameter is that it's a free parameter in this family of fuzzballs, right? In this family of solutions. When it's strictly larger than 0, the geometry has no horizon. So it's always going to be a horizonless geometry when it's strictly larger than 0. But as you get smaller and smaller, as lambda gets smaller and smaller, you approach or approximate the black hole geometry more and more. And in a sort of a discontinuous limit towards lambda equals to 0, the lambda equals to 0 limit is really the black hole geometry. So then you really do have a horizon and you have an actual black hole. Okay, but so as long as lambda is strictly larger than 0, you have no horizon, no black hole, and you have one of these fuzzballs, right? But so lambda sort of tells you how far away from the black hole limit your geometry will be or will behave. And indeed, we see that, so in this 4-color screen, the main thing to realize or to see is that geodesics, right, or light rays that probe the scale that we thought was the horizon, right, the would-be horizon scale, which is everything sort of inside of the would-be horizon of the black hole, right? So everything inside here, we see that these null rays or geodesics follow very chaotic orbits, right? And so the chaoticness of this orbit, you can see from the fact that these colors are very, very rapidly changing as we move around, right? So these orbits are very, very chaotic. And moreover, these orbits are very long-lived, okay? So the orbit is very chaotic and it takes the geodesic a long coordinate time, right? Asymptotic coordinate time to escape the microstructure, okay? So that's what's plotted here. This is, in fact, the coordinate time that the geodesic needs, right? Every pixel is colored according to the coordinate time that the geodesic needs to escape the microstructure. And so the more yellow it is, the longer it takes. Of course, if it enters into the black hole horizon here all the way on the right, then it takes infinity to escape because it can't escape. But any other geodesic will actually escape in some finite but very, very large time. And you can see that as you approach this black hole limit, the geodesics take even longer and longer and longer to escape these chaotic orbits. So that's the second row here. The third and fourth row show you that in addition to being chaotic orbits that take a long time to escape, these orbits are also orbits that experience a very large redshift, so that's what's plotted here, and a very large stress, tidal stress or curvature. Okay, and so basically in the third row here, you see the redshift encountered by each geodesic. And you see that, again, all of these geodesics that explore the microstructure at the would-be horizon, they explore a large redshift along their trajectory. And the same is true for tidal stress, right? These geodesics really encounter lots of tidal stress, as you can see from the lightening of the pixels here. Okay, so taken all together, the idea is that these are chaotic orbits. Okay, so to summarize, right, these are chaotic orbits, right? The stuff that goes into the horizon scale microstructure are geodesics that follow chaotic orbits that are long-lived. They have a long time they're orbiting for a long time. They encounter a high redshift and high tidal forces. And so this is how we like to argue that the fuzzball geometry looks effectively black. Okay, because really what's going to happen, of course, is that these geodesics or these light rays, because they encounter lots of tidal forces for a long period of time, the geodesic approximation will break down after a while. And so these tidal forces will show us that we need to take into account back reaction. And in the end, the geodesics, the light rays, will cause some kind of excitation of the fuzzball geometry. And then this excitation will want to emit some photons of its own, for example, and so on and so on. And in the end, what's going to come out of the fuzzball, what's going to come out of the microstructure is going to be photons that are emitted from a very high redshift region. And so there's going to be very highly redshifted photons coming out, but that's it. And so that's why it'll be effectively black, although it won't be completely black because you still have these high redshift photons coming out. Okay, so that's sort of how a fuzzball mimics a black hole and mimics this effective blackness, even though it doesn't have a horizon. It has, with using a buzzword, an emerging horizon. Now, I'd like to say just a few words about the observability about these of these objects, right? And so what we've done here, these are 4 panels. Everything except for the bottom right is an actual fuzzball, is one of these 4-color screen images. But instead of just taking the 4-color screen image, we darken each pixel according to the redshift that the geodesic encounters. And so in particular, the stuff that the geodesics that travel in the microstructure are going to be darkened because they encounter a lot of redshift. Okay, this is sort of a proxy because we don't have the full calculation available, of course, with the back reaction and the absorption and re-emission of photons, et cetera. This would be very hard. So we use the redshift as a proxy, sort of, as to understand how dark this shadow would look like, right? The inside would look like. And so using these proxy darkened geometries, we can do rough diagnostics using sort of the 2 rough diagnostics of EHT observations, which is the size of the shadow, which EHT has confirmed within 10%, and also the brightness at the center of the image, so at the center of the shadow, where EHT places a rough bound of about 10% of the brightness of the rest of the image. And so using these, using the first rough diagnostic, you can see that the top left here is sort of disqualified as a good black hole picture. When I compare it to the bottom right, which is the actual black hole, the top right here is just within the right brightness range, right? It's just within 10% in the center. But maybe most importantly is this this bottom left guy here is also a fuzzball, but it is virtually indistinguishable from the bottom right actual black hole. And so the only thing that this really shows is that, fuzzballs have a wide range of parameter space, right? They're very rich solutions, rich families of solutions. And by doing these rough diagnostics, we can already sort of cut out part of the parameter space as allowed regions in observations, but there will still be a large region that's still allowed by observations. Okay, now maybe a final remark on the observability. Something that was already talked about in the first talk was these photon rings being very precise measures of the geometry, which sort of circumvent the problems and the uncertainty in the plasma physics of images of black holes. So I won't discuss this at length, but I just want to say that this is indeed something that might be exciting as well for fuzzballs to study these higher order photon rings and to understand whether, for which range of parameters, et cetera, can they be distinguished from their black hole partners. And so first step in this direction is a work that's almost finished by our collaboration, where we're just looking at simply Kerr versus Kerr-Newman, right? When we assume that the Kerr-Newman charge of the black hole is dark, right? So it doesn't interact with the photons except gravitationally. And then the question is, can we distinguish between Kerr and Kerr-Newman images based on the properties of the photon rings? Okay, so I just want to very briefly summarize the ideas that I talked about here were about fuzzballs, and I showed you hopefully somewhat convincingly that they can mimic black holes arbitrarily well, and they show this feature of emerging horizons, even though they don't have a horizon themselves. And then I think it's a very exciting thing to study how observations can restrict the allowed parameter range of these fuzzball geometries. And so as a general principle, as a general thing, I would like to advertise this idea of fuzzball phenomenology, right? These are top-down quantum gravity motivated exotic compact objects. And so it's sort of a really new thing since last year. I think the first studies of fuzzball phenomenology have started. And I think this is a very new field with many things left to be done, many insights left to be had. And so I think this is very exciting. Okay, thanks.
Thank you very much. Okay, there's already a question by Frederick.
Yeah, thank you very much for the very nice talk. I have a naive question because I don't know anything about fuzzball. I didn't know anything 20 minutes ago. So I understand that there is this lambda parameter. So if I understand well, it has to be big enough in order to be able to solve this information paradox, but it has to be small enough in order to be able to mimic the black hole. So do you have some space in between? Are you, I don't know, you know?
Right. Yes, thanks for the question. Yeah, I unfortunately I wasn't able to talk more about the scaling parameter. Actually, in a very theoretical sense, smaller is almost better for the theory. And so when so there's this whole game in string theory that you can count the number of fuzzball solutions for a given black hole, and you should be able to reproduce the black hole entropy given the amount of fuzzballs that you have. But when you're counting these fuzzballs, most of them will be at infinitesimally small lambda, basically. So actually, from a theoretical perspective, I think small lambda is not a problem and is even preferred. Yeah, it's just that, of course, as you can decrease lambda arbitrarily much, maybe it's bounded by some Planck scale or something like that. But unfortunately, as you decrease lambda more and more, you can always sort of get within observable bounds, right? It'll be mimicking the black hole arbitrarily well, and so you won't be able to distinguish it. So from that point of view, that would be unfortunate.
Okay, there's another question by Mikolai.
Hello, it's Mikołaj Korzyński here from Center for Theoretical Physics in Warsaw. So it's also my first exposure to the fuzzball paradigm. And I have a simple question. At some point, you mentioned that some of the geodesics before returning back to infinity are affected by high redshift. If I understand correctly, what you mean is that your solutions are somewhat static or stationary. So you've got some kind of killing field which defines the local static observers, and that somehow it passes through regions where the redshift with respect to these observers is high, because when the geodesic goes back, you are back to standard redshift. Is it correct?
Yes, that's correct. Yes.
Okay, thanks.
Yes. So in particular, maybe, I mean, this is probably where the question's coming from, right? The geodesics will start out from infinity where the redshift is just, let's say 1, right? If we think of GTT, and then they travel into a region of high redshift. But then, of course, when they come out, they are blue shifted again into normal, or they blue shift first and then they redshift back out. The idea is that this process is going to be a multi-step process where the photon is absorbed and then highly redshifted photons are emitted from these regions of high redshift, and that's why we say this contributes to the blackness of the image.
Okay, thanks.
Okay, I'm afraid that we have to move on. I apologize to the two people who want to ask questions, but I'm afraid that we don't have any time. So I want to thank you again for this talk, Daniel. And the next speaker is Carla Zederbaum. That's an invited talk. and she claims that static equipotential photon surfaces have no hair. Please, Carla.
Thanks very much, and thanks for the invitation and for all the interesting talks I've been able to hear so far. We'll switch gears now to a more theoretical perspective and actually not consider stationary but only static spacetimes in this talk. I may be able to say a few words of outlook towards the stationary case towards the end if you're interested. So I would like to recall that, of course, everybody knows the Schwarzschild-Tangellini spacetime, and I'm mostly writing this down to introduce notation. So the Schwarzschild or Schwarzschild-Tangellini spacetimes in 1 plus n spacetime dimensions looks like this, or it's metric rather, and d omega squared is my notation for the canonical metric on the sphere. And it's well known, of course, and we've heard it already alluded to today, that if the mass is positive, then there's a photon sphere cylinder at a certain radius in 3 spatial dimensions. You're familiar with this photon sphere sitting at r equals 3m. In higher dimensions, this is the formula that, this is the formula that produces the very same phenomenon, okay, for positive mass, and n is the spatial dimension here. In 2003, Frederick Vancer and Volker Perlich have considered this spacetime in the case of n equals 2, so where the sphere is just a circle. And they have constructed a plethora of spherically symmetric so-called photon surfaces. Where here by a photon surface, I mean an umbilic time-like surface. So just like the photon sphere would be one of the examples. Now here we have 2 spatial dimensions in 1 time direction, but they found a lot more than just the cylindrical ones. And the definition, the mathematical definition of a photon surface here can be worded either as an umbilic time-like surface, where umbilic means that the extrinsic curvature is proportional to the induced metric along this hypersurface. And if this is not so intuitive to you, a logically equivalent formulation is saying it's a time-like surface along which any null geodesic that's ever tangent to it stays tangent to it as long as it exists. Okay, this is true for the photon sphere, but they found for n equals 2 in this Schwarzschild-Tangellini generalization to 2 spatial dimensions, they found a whole zoo of such spherically symmetric photon surfaces. And I have a picture here that I'll enlarge for you that we drew, we reproduced from their work. So the red line R star is the photon sphere in an RT diagram here, R being the radial coordinate in the Schwarzschild of whatever dimension we're looking at, and T being the time coordinate, and the angles are suppressed here. So we're just drawing the radial profiles. And so they find curves, radial profiles of rotationally symmetric photon surfaces of the kind that comes in from, that comes in from tangentially to the photon sphere and goes out to infinity, or another type that they find photon surfaces, that emerge from somehow tangentially to the horizon, then bump around and go back tangentially to the horizon, and another kind that looks like this. It looks like more or less like the radial profile looks more or less like a hyperbola, coming in from infinity and moving back out to infinity. So these are the radial profiles, let me stress this again, of the rotationally symmetric photon surfaces identified in 2 spatial dimensions Schwarzschild by Frederick Vancer and Perlich. And others can come in, from the black hole horizon and then move away to infinity. And all of these also exist in their time reflected versions, and they also all exist in their time translated versions. And this is due to the time translation and time reflection invariance of the Schwarzschild spacetime. I forgot to mention one type. There's this one type which I should have probably drawn here. So we have this one type that comes from the horizon and asymptotes the photon sphere, and this other type that I drew in the wrong picture, which comes from the horizon, turns around and goes back tangentially to the horizon in this way of depicting it. Okay, so these are the different types of photon surfaces that they find. And what I've looked at together with Greg Galloway in a work that's recently been published is that it is the higher dimensional case. So the case where we have at least 3 spatial dimensions. And here is a list of the results that we find. So first of all, we find the exact same plethora, the exact same zoo of rotationally symmetric photon surfaces I just explained to you in these higher spatial dimensions, in particular in the 4-dimensional space-time case, where again here a photon surface is defined as an umbilic time-like now hypersurface. And more generally, we find the exact same phenomenology in spacetimes of this form here, where you know that this of course includes Schwarzschild, but it also includes anti-de Sitter, it also includes Reisner-Nordström and many other examples, and we call those spacetimes of class S. And we find that a spacetime of this form has a photon sphere at a given radius r star, if and only if the function f at this r star satisfies this condition. And also it has a rotationally symmetric photon sphere, so photon surface, sorry, with radial profile r, if and only if this radial profile satisfies this ODE, where lambda is some positive parameter related to the umbilicity factor. It's exactly the umbilicity factor for those who know what this means. So the picture in a generic space-time of this class S looks exactly the same. So I'm not going to discuss it again. In case there is exactly one solution of this photon sphere ODE here, and I'll say more about this. So we find the exact picture in particular in higher dimensional Schwarzschild-Tangerlini starting in 4 space-time dimensions. Okay. So what else do we understand in this class S? We understand, on top of what I just said, that there aren't only rotationally symmetric photon surfaces, but there are also others which look like partial hyperplanes. Think of the Schwarzschild spacetime in an RT diagram now with angles. And if I cut a plane that contains the t-axis, of course it doesn't have an interior because of the black hole, but if I cut a plane in here containing the t-axis and keep the piece, the partial hyperplane, sitting outside the black hole, then this is also a photon surface by symmetry. But in all, and this happens in all these spacetimes in class S, and we can show that every photon surface is either rotationally symmetric or such a partial hyperplane, provided that the spacetime is nowhere conformal to Minkowski. Being conformal to Minkowski, meaning having the same angles as in Minkowski, is problematic because in Minkowski, you have the photon surfaces which are all time-like planes and all time-like one-sheeted hyperboloids, and they can be translated, and we cannot account for this translation in this conformal picture. That's why we have to make this orange restriction. Furthermore, we can show that if you're in a static spacetime of this form minus n squared dt squared plus g, where g is some spatial metric independent of the time, and n is my name for the lapse function here, and we are in spatial dimensions 1 plus n greater or equal to 1 plus 3, and we vacuum and asymptotically Schwarzschild, I forgot to say that. Here. Then we have the following theorem. If the inner boundary of this static vacuum spacetime, which is asymptotic to Schwarzschild or Schwarzschild-Tangerlini in higher dimensions, if it has an inner boundary, and the boundary consists of multiple components, each of which is either a black hole horizon or photon surface, or for example, as a special case, a photon sphere, under this condition that the photon surface's boundary components are equipotential, I'll say in a moment what this means, then the spacetime is actually Schwarzschild-Tangerlini. So this is what I understand would be called a no Hair theorem in the physics community. So let me rephrase it as a no Hair theorem before I explain what this condition of equipotential is. So a no Hair theorem, it is a no Hair theorem in the following sense. If I have a static configuration of black holes, 0 black holes, 1 or more, and photon spheres and photon surfaces. And here I'm not visualizing them inside each other because all of them are boundary components. So they all sit next to each other. So I have a black hole here, maybe a photon sphere here, and another equipotential photon surface here. Then there's at most one of them, either a black hole or photon sphere or one of these equipotential photon surfaces. And the exterior region to it is exactly Schwarzschild or Schwarzschild-Tangerlini in higher dimensions. So I have no freedom, they have no hair whatsoever. So I still owe you an explanation of the term equipotential, which is an important assumption in this theorem that we cannot get rid of, it seems, at the moment at least, partially because of the existence of these partial hyperplanes, even in the Schwarzschild-Tangerlini spacetime, which are photon surfaces. So here's the definition of equipotential. If I have a photon surface, like in this picture, the green surface, it's a time-like umbilic hypersurface, and I intersect it in the static spacetime with a t equals constant slice. So any of the slices orthogonal to the Killing vector field, then I want the Lapse function to be constant on this cross-section. In other words, the Lapse function along the photon surface can only depend on its time component, not its spatial component. So in some sense, if you want, you can write this as n, the Lapse function being a function of t along the photon surface. Okay. And this is, of course, given if I'm in a photon sphere case where I'm really a cylinder, where n is the Lapse function is actually constant along the photon surface, and is of course given in any spacetime of class S, so any spherically symmetric static spacetime for spherically symmetric photon surfaces, because then I have this condition satisfied a priori. So in my Schwarzschild-Tangerlini examples, it's satisfied exactly by the rotationally symmetric photon surfaces that I want to find in this case as inner boundary components. Okay, and I'm ruling out in Schwarzschild-Tangerlini these partial hyperplanes, which are also not boundary components, but in that case, but I'm ruling out this phenomenon. Another thing we can show, which maybe is more close to things that people here in this virtual room consider, is that rotationally symmetric photon surfaces in spacetimes of class S are actually the same thing as time-like hypersurface generated by null geodesics via rotation. So if I have any null geodesic with vanishing angular momentum, and I rotate it in space and around all the sphere of the spherical symmetry, then it creates a time-like hypersurface. And this time-like hypersurface will be a rotationally symmetric photon surface, and every rotationally symmetric photon surface will be generated this way. And the parameter lambda, the positive umbilicity parameter that appeared in the photon surface ODE, can be related to the energy and the angular momentum of the generating null geodesic in this way. So it's actually nothing else but E over L. So it's not a funny geometric parameter only, it's also very closely related to the conserved charges along the null geodesic, generating this photon surface, this rotationally symmetric one. And this insight allows us to show that the null section of the phase space of a spacetime of class S is actually partitioned by rotationally symmetric photon surfaces and rotationally symmetric principal null hypersurfaces. Those are those null hypersurfaces generated by rotation by null geodesics with angular momentum 0. So every null geodesic either has angular momentum 0 and then by rotation generalizes it generates a principal null hypersurface, or has non-zero angular momentum, and then by rotation generates a rotationally symmetric photon surface. Okay, so having these insights at the back of our mind, there's work in progress I'm about to write up with my PhD student Markus Wolf, where we generalize all the above discussion and analysis to the case where here in the last part of my metric, instead of just looking at the sphere with its canonical metric, we can look at an arbitrary n-1 dimensional Riemannian manifold, maybe more of mathematical interest. But we can also construct Kruskal-Saccharis extensions, as those you know for the Schwarzschild spacetime, in all those, in all these metrics in class H, which encompasses the class S we've looked at before, if they have across any non-degenerate killing horizons they may have. And this allows us to actually consider what happens to these rotationally symmetric photon surfaces that we discussed previously if I look at those that approach the horizon. Yeah, here, so on the right-hand side here, I've drawn a little reminder of the picture that looked much more professional that we looked at in the beginning. And it turns out that the purple and green rotational profiles drawn on the right-hand side here in the TR diagram that appear to actually asymptote to the horizon actually penetrate the black hole and only look as if they asymptote to the horizon because we look at them in TR coordinates and not in Kruskal-Saccharis coordinates. As soon as we do so, we see that they penetrate the horizon. And those like the blue ones who look like they asymptote to the rotational hyperboloids in Minkowski spacetime in the TR diagram actually can be shown to do so when we use in a very strong sense in Kruskal-Saccharis coordinates. And this doesn't only apply to Schwarzschild, but in particular, it does apply to Schwarzschild and Schwarzschild-Tangellini, starting in spatial dimension 3. But the same should be true for lower spatial dimensions as well. And just to complement this with work in progress with my former student, Sophia Jans, and my current student, Olivia Vicanic-Martinez, what we've looked at is, again, this photon surface ODE that I've shown you before, where the parameter lambda was the embellicity parameter, or in other words, the energy divided by the angular momentum for the generating null geodesic of the rotationally symmetric photon surface. And in order to study how this ODE behaves in a more generic profile F was the function in the metric minus f of r t squared. Yeah. So this profile, we've by analogy to this null geodesic analysis, we introduce this effective potential f of r divided by r squared. And then for Schwarzschild, of course, this effective potential looks as in this diagram here. And the different values of lambda actually correspond nicely to different energy levels in this effective potential diagram, which allows us to give a rigorous analysis and ensure that the picture we've seen earlier with all these nice profile curves actually is complete, and we haven't overlooked anything. And all these radial profiles are smooth, and this holds for any space-time with radial profile taking roughly this form. So it has a non-degenerate killing horizon here. That doesn't work. Then here, and decays. The effective potential decays to 0 near infinity. But we can also generalize this analysis to other situations where the asymptotics is different, for example, or where we have multiple turning points. Here, this turning point corresponds to the photon sphere of this maximum. Yeah? So we can do this analysis in the wide variety of spacetimes of class S, also in this more general class H that I mentioned before, and this class includes Schwarzschild, Tangellini, Reisner, Nordstrom in spatial dimensions larger or equal to 3, ADS Schwarzschild, ADS Reisner-Nordström, and also Kotler spacetimes with different spatial cross sections. And we can also generalize the Hair theorem to asymptotically flat unique electrovacuum in this paper. Thanks very much.
Okay, thank you very much for the talk. And yeah, maybe we can allow ourselves one question. Is there a question? See any? But I have one. Do you see a chance to generalize your Hair theorem to the rotating case beyond spherical symmetry?
Now, at the moment, we don't see a clear statement that we could hope to be true in the non-static case, actually, because we wouldn't expect the trapped photons to live on a hypersurface in the space-time, right? Even in Kerr, they don't do that. There's this expanded photon region, and you have to live to the phase space in order to get a nice smooth submanifold even. Yeah. So I don't see how this could be approached in the manifold itself, and we're still dreaming that we can approach it in the phase space. But then it's not a hypersurface, but a 5-dimensional and an 8-dimensional, and then it's not really clear what types of techniques one can use. Yeah. But we do hope that we can get some like quasi-local information near trapped photons, or maybe at least for small angular parameters, say in the Kerr family, understand what happens to the non-photon sphere photon surfaces, if anything persists.
Yeah, I have exactly the same impression, yes. Okay, thank you very much again for your talk. I think we should move on.
Thanks.
Now we have, as the last two speakers are actually two young colleagues of myself. So the first of them is Murat Haller, and he is going to speak on a more theoretical analysis of gravitational lensing by rotating traversable wormholes. Please, Murat.
Thank you very much. Can you hear me?
Yes, we hear you.
Thank you very much to give me time to speak about more theoretical analysis of gravitational lensing by rotating reversible wormhole. I do this work in collaboration with Volker Pellick. My talk look like this. I begin with motivation, why Morse theory for gravitational lensing. Then I will speak about rotating the reversible wormhole. Then with the help of global hyperbolicity of the metric, we show that the metric also admits the metric graph condition. Then I will show how we can calculate initial forces. And with this help, with these forces, we can decompose the space-time in the region, and we show where is the rotating like geodesics. Then I will give example at the end. I will apply Morse theory to find multiple imaging. Why Morse theory for gravitational lensing? Because if we have point in the space-time P as observer and time-like curve gamma, the question of how many images an observer at an event P see of light source with word line gamma is equivalent to the question of how many paths pointing like geodesic from P to gamma. In space-time with many symmetry, we can do this easy with directly integrating the geodesic equation. Sometimes is elliptic integral. But the problem, if the light source are not static, then we can use indirect method to solve this problem, like Morse theory. And Morse theory in general relates the number of the solutions to variational principle to the topology of the space of 3N map. 3N map is the maps are the light-like curve joining a point P and time-like curve gamma in space-time M. I give just general what is rotating to reversible wormhole. You can find more detail in this original paper. We know that in the wormhole there are no event horizons or curvature singularities. Stationary axial and axis symmetric metric into the form suitable for describing rotating reversible wormhole given by this metric, where n here is Lip's function and r is measured at point L from L and theta from the origin, and omega is the angular velocity. And in this metric, L defined everywhere. And with this, the wormhole represented by this metric maybe have also arbitrarily many throats. It is easy to prove that the wormhole metric is global hyperbolic. We know that in global hyperbolic manifold admits the foliation into the space-time, where sigma 3-dimension surface is a smooth Cauchy surface. This product can be chosen such that the metric is orthogonal split into spatial and temporal part, where x in this metric here are independent time coordinate on Cauchy surface. The idea that we say that splitting satisfies the metric condition if for every compact subset of Cauchy surface there are function f, this function satisfies this equation here, such that for t less than 0, then we have this inequality here, and this inequality holds for all x in the compact subset with time-independent Riemannian metric G. You can find a more mathematical proof in this paper. Why is the metric condition is important? Because it prohibits the existence of particle horizon. This means from each point P in M, one can find path pointing like curve to every time-like curve that is vertical with respect to the orthogonal splitting chosen. And we will show this later that we need metric condition to apply Morse theory. Now we want to apply this, we want to prove that the metric wormhole is admit the metric condition. We know in the wormhole metric, like Kerr metric or something, the T line are not orthogonal to surface T constant. We can find this just we change the new coordinates. This is ansatz. Then the rotating reversible wormhole take the orthogonal splitting form with H metric and F in this here. And if with some calculation, if we restrict the range of the coordinate x to the compact set, we can find positive constant A and B, such that the inequality of the metric graph condition satisfies. Therefore, we can say that the wormhole satisfies the metric graph condition. Now I want to show how we can calculate initial forces in the wormhole. And we take the word line of the observer will circle along three lines. This is given with this equation here, where in this equation, I is the orthonormal basis, and V is give the velocity. This velocity is of the observer with respect to standard observer. Integral curve of U are parameterized by the proper time. And in this equation here for upper sine, the motion relative to the standard observer in the positive direction and those co-rotating. And for negative sign, it is negative direction and those contour-rotating. In general, U is no geodesic. This means covariant derivative not equal to 0, and one need throws to stay on the integral curve of U. And the initial acceleration is of freely falling particle relative to the U observer is given with this equation here. And we know that multiplication with the particles mass give the corresponding initial forces. There are some rules like Newtonian mechanic, that gravitational acceleration independent of the velocity, and Coriolis acceleration odd with respect to velocity, and centrifugal acceleration even with respect to velocity. And with help this force, we want to find some potential up to positive factor. This factor, the sum of Coriolis and centrifugal acceleration is equal this equation here. We need something depend to velocity. Therefore, is gravitational acceleration is not included in this equation. To investigate the behavior of velocity close to the velocity of the light, we consider the limit that and with this limit, we find this potential here. And this potential is are relevant for lensing because we will show that tell us where the radius coordinate L has a minima or maxima along like geodesic. And with this potential, also we can find, if we fix a theta, we can find also photon circles. We can fix, for example, for equatorial plane. With definition, we decompose our region M. We define in M in that where the derivative of C plus and C minus less than 0, and in M out where the derivative of C plus and C minus bigger 0, and K minus and K plus where the sign are changed. With the help of this definition, we can find, we can easily prove this proposition. We find that in the region M out, the radius coordinate L cannot have other extrema than strict local minima along like geodesics. And in the region M in, the radius coordinate L cannot have other extrema than strict local maxima along like geodesics. And it's important that through each point of K plus and K minus, that is spherical like geodesics. This means the geodesics is completely contained in the sphere with L equal constant. It is easy to prove this proposition if we take X light and geodesic vector field, and we have to prove in M out that 2-time derivative of L bigger 0, and we have to show also that in M in that the 2-time derivative L less than 0, and for region K, we have to show that the covariant derivative of X equal to 0. Now, in the wormhole, how is in practice how this region look like? We have two cases in the wormhole. In the first case here we see that the region can be connected. For example, for K plus, we have also K plus in this region here. And also there are second example that this region cannot connected. Like, for example, we see K plus here, K minus here, and K minus here. And we take in this plot that L equal minus infinity at the origin. Now I want to speak about multiple imaging in the wormhole. Now we fix a point P and timeline curve, gamma and M, and we want to get some information about the path pointing like geodesic from P to gamma. It is easy to prove this proposition. This proposition tells us to what region the light geodesic between P and gamma are confined. This proposition tells us that we begin with, we show that P be an event and gamma pass inextensible time-like curve on which absolute value remain bounded in the time coordinate t. If we send t to minus infinity along gamma, it is easy to prove that we can find the smallest shell between two radius L1 and L2, which is guaranteed that we can find P and gamma and the region K in this spherical shell. The proof is easy because along like geodesics that leave and re-enter the spherical shell, the radius coordinate must have either maxima in the region M out or a minimum in the region M in. And with the help of the proposition before, this cannot be happen because in the proposition 1, in the region M out, the radius coordinate I cannot have other extrema than strict local minima, and in M out, the radius coordinate I cannot have other extrema than strict local maxima along like geodesy. This proposition tells us to what region the light geodesic between P and gamma are confined, but it does not tell us anything about the number of this geodesic. To see the number of the geodesic between P and gamma, we introduce Uhlenbeck theorem. Uhlenbeck theorem tells us that if we take space-time, global hyperbolic space-time that admits orthogonal splitting, we have seen before that the metric, the wormhole metric accept this condition. If the splitting satisfies the metric condition, and if we take curve beta and we fix point P in M, and we take smooth curve in M, and with the splitting, take this form here, and we assume that gamma does not meet the caustic of the past light cone of P. Then we can find for some sequence tau I, if we send tau I to minus infinity, is guaranteed that sequence beta I is converged in Cauchy surface sigma. Then the Morse inequality tells us that n kappa is bigger or equal b kappa for all kappa is element from n, and then the Morse relation tell us Morse relation take this equation here, and this equation where and denote the number of path pointing like geodesics with index kappa from P to gamma, and B is B kappa is denote the kappa Bethe number of the loop space of M. And with this Morse theory, we relate the number of path pointing like geodesics with beta, with the topology of our space-time. You can also find the proof in the same paper. The idea to apply this in wormhole, we have proved this before, and we take a smooth future pointing time like curve gamma with the TI take a value between minus infinity plus infinity. We parameterize we take the parameterized such that the t coordinate of the point gamma is equal to tau, and we have to prove because of the convergence in this theorem that for tau, if we send tau to minus infinity, the radius coordinate L of point gamma does not go to plus infinity or minus infinity. The Bethe number of the loop space of M are of course determined by the topology of Cauchy surface. The domain of the wormhole has topology S2 R2, where S2 is the two sphere. This means that M is simply connected but not contractible to a point. Then for all but infinity many kappa, we have Bethe number as big as 0. This means almost every positive integral interior kappa, we can find path pointing like light geodesic from P to gamma with kappa conjugate point in its interior. This means also that there must be infinity many paths pointing like light geodesic from P to gamma. And with the help of this theorem and proposition before, proposition 2, we can easily prove that if we take U any open subset in spherical shell lambda that contain the region K, then all but infinity many paths pointing like light geodesic from P to gamma intersect this open subset U. You can find the proof in this mathematical proof in this paper here. As conclusion, we can say that in the rotating traversable wormhole, the occurrence of infinitely many images is intimately related than the occurrence of the centrifugal plus Coriolis forces reversing. Thank you very much.
Okay, thank you, Murat. I think we should allow ourselves time for one question. Alexander.
Probably it's a naive question, but it seems to me that is some kind of generalization of Hasse and Volcker theorem for this case. And in this case, there is a question, what about observable properties? I mean, if you substitute, for instance, rotating a black hole with a rotating wormhole, some multiple images, differences in multiple images or shadow or something like this. Did you evaluate these effects or not?
I mean, for example, our paper from Berlik in Carriage Newman, we don't have we have just connected the region, and in wormhole is important in wormhole that we have also that not connected region.
Yeah, this was a response to your first remark. So it's really a non-trivial generalization. So what we did in what Wolfgang and I did in 2006, this was just for the Newman metric. And the situation is here, it can really be very much more general as these pictures show. So it is really a non-trivial generalization of this. And the second part of your remark, there's the observable features. Yeah, it's very difficult to distinguish wormholes from black holes. That's the lesson which we get from this approach and also from other approaches, right?
Okay, thank you.
Okay, thank you, Murat, again for your talk. And I think we should move on now. Now we have the last talk. This is by Torben Frost. And he's going to speak on gravitational lensing by charged accelerating black holes.
Okay. I hope you can see my screen now.
Yes, everything is fine.
Okay. So hello, everybody. Welcome to my talk. And thanks also for giving me the opportunity to give a talk here. And I will give a talk on gravitational lensing by charged accelerating black holes. And for this talk, my talk is structured as following. First, I give you a short motivation, then I give you a short overview about the charged zeta metric, and then I apply basically the solutions to the geodesic equations to gravitational lensing, and in the end, I will give you a short outlook. So what is the motivation behind my talk? As we all know, basically on large scales, the universe is electrically neutral. However, this may look basically quite different when we go into black holes, which are embedded in the plasma and in strong magnetic fields, so they can acquire quite large electric charge. In addition, as we see from the black hole mergers and the gravitational wave signals, black holes tend to move. And so we need somehow space-times for basically black hole space-time metrics that describe moving black holes. And one simple example is the charged zeta metric. So then why do I use gravitational lensing? Well, the explanation is quite simple. In 2019, the Event Horizon Telescope collaboration published the first result about the shadow in the galaxy M87. And so it allows testing strong gravity in very close to the black hole. And so I apply in this work basically analytical methods to describe lensing and the charge to the zeta metric. Here I will focus on the lens map and the travel time and the redshift set. So here on this slide, I give you the linear length of the charge to the zeta metric, and we can see it's basically the Reissner-Nordström line element modified by the acceleration parameter alpha and the cosmological constant, and adding the acceleration parameter and the cosmological constant to the metric adds to the inner and outer black hole horizon simply another horizon, which indicates is that alpha is quite large, then it's an acceleration horizon, and when lambda is relatively large, then it's a cosmological horizon. Then the metric itself is a solution of Einstein's electrovacuum field equations with the cosmological constant. It's axisymmetric and static, so it's not spherically symmetric anymore as a Schwarzschild spacetime or the Reissner-Nordström spacetime. And in the case that the charge is not zero, we have here the time-like curvature singularity at r equals 0. Then one particular interesting part in this metric is when we transform alpha to minus alpha and mirror again at theta equal pi12, then we transform the metric back into itself. So we can restrict our investigation to alpha bigger 0. And another point which we have to consider is that for the r coordinate, when we have the prefactor omega equal to 0, this corresponds to conformal infinity. So the r coordinate doesn't range from r equals 0 to r equal infinity, but to a finite value of r. Then the theta and phi coordinates in my work, I assume that they are basically the coordinates on the two-sphere. And one speciality in this metric, or one mathematical peculiarity, is that we have conical singularities on the axis, which lead to a deficit angle for theta equal theta smaller than pi12, and a surplus angle for theta bigger than pi12. Then in the next step, I separated the equations of motion, where I introduced the three constants of motion, the energy E, the angular momentum Lz, and the Katze constant. In the C matrix in general, this is only possible for lifelike geodesics. So we have always that the Lagrangian is L equals 0. And here, in addition, I introduced this lambda parameter, which is usually known as minor parameter, but it's, since Alexander Zakharov mentioned it, I think 1 or 2 weeks ago, he used it already before. Then in the next step, basically I analyze where we have this unstable photon orbits. They require the r by the lambda and d square r by the lambda square equals 0. And in the case of the charge to the zeta metric, this is the solution of a polynomial of third order. And what we see here, basically the cosmological constant lambda has no influence. So this remains the same as in the spherically symmetric spacetimes. In general, we have only one exact, basically, in the region we are interested in, we have only one solution. So we have, in the region of outer communication, we have one exact arc photon. And when we reduce this for the symmetric case, so we set E equals 0, the solution can also be found in Ares Alavadi and in my paper together with Volker Perlik, where we simply have to solve this polynomial of second order and we get an exact result. Here, for the polynomial of third order, we simply can also get these exact results with the Cardano's method. However, their solutions don't really look very beautiful. And if we consider basically motion in the symmetric, or in the symmetrics, we have a maximum between the outer black hole horizon and the photon sphere. And in the region we are interested in, we have always a minimum between the photon sphere and the acceleration / cosmological horizon. The next step is we have to also look at the theta motion. So here we have also the specialty that we have basically unstable photon orbits. Here we have to require that the theta by the lambda is equal to d squared theta by the lambda square is equal to 0. And when we apply this to the charge series zeta metric, we get again a polynomial of third order. And we can solve this using Cardano's formula again. And here we get that in all cases of the symmetric, we have a single cone with constant angle theta photon. And when we have photons traveling, light geodesics traveling on this photon cone, they stay on this photon cone. This, for the symmetric, was also already found in the paper of Alavadi et al. However, Volker actually found this much earlier. We just didn't manage to publish this result. Unfortunately, we didn't manage to publish the result earlier. And in the symmetrics, we have basically the motion is bound between theta min and theta max, which can also reach the axis when we assume that the axes are transparent. So now I go on to the gravitational lensing. Here, I fixed first an observer in the direction of outer communication between the photon sphere and the outer horizon, and basically introduced an orthonormal tetrad following the approach from Grenzebach et al. And here we have E0, which is basically the fall velocity of the observer, and E3 is the negative E3 direction marks sigma, so the celestial coordinate sigma 0, and psi will then be, or second latitudinal coordinate will then rotate around the axis. Then I introduce a tangent vector. In general, it can be written like this formulation. And I also introduced, following also the approach from Arne Grenzenbach, a tangent vector at the position of the observer, which is then given in terms of the tetrad and the celestial coordinate sigma and psi as provided here, where sigma is a normalization constant, which we in general can choose by this term. And then we can relate the constants of motion E, L, Z, and K to the position of the observer in a radius and latitude coordinates and the angles on the celestial sphere here below. In the next step, I constructed the lens map following the approach of Fritelli and Newman, or as done by Volker Perlich in this work in 2004, which then projects from the celestial coordinates to theta L and phi L, which are then depending on sigma and psi. So here, I first shoot light rays backward into the past from the position of the observer until it intersects the sphere of the light sources and calculate the minor parameter lambda L. Here, since the matrix has scaling vectors dt and d phi, we can choose TO and phi O equals 0. And we always choose lambda O equals 0, which is then bigger lambda L. In the first step, I calculate the minor parameter. Then in the second step, I calculate the turning points of the theta motion, since in general we can have arbitrarily many turning points. And then I calculated theta L and phi L using elliptic integrals and elliptic functions. For projecting basically everything, I applied the convention followed in introduced in the paper of Boson et al. So that we have red and green for geodesics above pi half, and yellow and blue for geodesics below pi half. And here we have pi equals 0, so we have green and blue for phi L equals 0 and between 0 and pi, and we have red and yellow for geodesics between pi and 2 pi. Here we have an example image for the lens map in the Reisner-Nordström and the Reisner-Nordström de Sitter metric. Reisner-Nordström is on the left. We can see here green and blue always form image of one order. Here we have the first order. Here we have the second order. When we go further, and here we have the third order. And even further, and here we have the fourth order. Again, also for red and yellow. First order, second order, third order, fourth order. And in this case, I use the extremal case for the Reisner-Nordström metric. On the right-hand side, when we turn on the cosmological constant, we see immediately that the shadow, which we have here in the center, shrinks, but otherwise, basically, the whole construct is the same. So if we want to measure it, we can, without knowing precise distances, we cannot distinguish which metric is which, or which image we see is from which metric. Then I turn on the acceleration parameter, and we can see basically first, when we see here pi half and 3 pi half psi, we have this is the I call the northern hemisphere, this is the southern hemisphere, and we can see when we are in the equatorial plane, so theta O equal pi half, we don't have symmetry anymore to the equatorial plane on the sky, which is completely different to spherically symmetric metrics. And also here in the center, we see the whole structure changes. Here above, we can see that images of second order, which is basically this field, appears already further away from the shadow. So here we have the string. So we basically on the string, we have two continuations, and this leads due to the deficit angle that here basically the light ray covers the T5 faster. On the other hand, on the lower side, it's opposite slow. And if we go then to the symmetric with most cosmological constant, we see it shrinks again, but the basic feature remains the same. Then I go to theta O equal pi fourths. Here we see it much more pronounced that these parts, the image of second order, appear even further away from the shadow than before. And we can here also see the structures. We can see up to images, in this case, as far as I remember, even fifth order, which are very, very close to the black hole shadow. And here we have the same image again for the charged CD zeta metric, where everything shrinks. So also here the features remain the same. Now I will turn to the redshift. Basically, the redshift factor relates the energy of a light, say, at the position of the light source to the energy of the light ray as detected by an observer. The formula to calculate this, since we have a static light source and a static observer, we can find in the book of Straumann, and it's given by this relation. And if we insert GTT at the position, evaluated at the position of the observer and of the light source, we get this relation. And if we plot this using theta L and R, we get this result. So we can see when we take the redshift from Schwarzschild and the Reissner-Nordström metric, which are both negative, we can immediately see here it's not constant anymore, but it's a function of z sigma psi. And we have here redshifts, basically mainly on the southern hemisphere, and we have a field of blue shifts on the northern hemisphere. Here we have another field of blue shifts. Here another redshift, and if we go further down, we will see here another region of blue shifts, redshifts, and so on. And if we go to the CD zeta metric, charged CD zeta metric, basically those regions shrink and are closer to the shadow. Then I also calculated the travel time, which basically measures in terms of the coordinate time, the time the light ray needs to travel from the light source to the observer. And I expressed this integral, which is a simple elliptic integral, which I can then transform to elliptic integrals of first, second, and third kind, and plotted this. Here we can see on the left-hand side a comparison between the Reissner-Nordström metric and the charged C metric in both cases for the extremal case. And we see here for the Reissner-Nordström metric up to close to the shadow, the travel time is always shorter, while for the charged C metric, it's always longer. And here we can also clearly see again, the shadow of the charged C metric is smaller. On the right-hand side, we turn on the cosmological constant, otherwise all parameters are the same. We see that here the difference is even more pronounced. So what do I conclude from my work? Well, basically first for the redshift and lens map, the angular diameter of the shadow shrinks, but it's still circular. So we cannot distinguish between circularly symmetric spacetimes and axisymmetric spacetimes based on the shadow alone. Since when we measure, we can have arbitrary distance, and we don't know a priori we can have any of these black holes. Then also the pattern basically which we have, which I didn't show for the C-metric and the C-metric, also there it remains the same. But if you compare it to the Reissner-Nordström metric, the Schwarzschild metric, the Kotler metric, which is the zeta metric, or the Reissner-Nordström, the zeta metric, the most striking differences appear close to the axis and very close to the axis. Then for the travel time, sorry, this is actually when we compare it to the C metric, it's very similar, but we see for when we go to the Reisner-Nordström metric, we see basically they are much longer when we turn on the acceleration parameter. And basically when we have just a low charge, which I didn't show yet, the travel time is shorter than without charge. Then what implications provide this for observations? Well, as I already mentioned, the shadow is circular and the dense map structure is similar for the symmetric. We can basically, without distance measures, we cannot determine the nature of the black holes. So we need additional distance measures. However, we can distinguish between accelerating black holes and spherically symmetric black holes when we go able to observe very closely to the axis, because here we can observe the most striking differences. Here is I end my talk, and here are also the references of my presentation. And thank you very much for your attention.
Yeah, thank you very much, Torben, for the talk. Questions or comments? Alexander, as usual, please.
So I want to join your talk, but it looks like joke, because I don't know, it sees that you could think that I'm asking to substitute Mina name with my one. It's not my message, but message is this transformation is rather trivial, very simple.
Yes.
It's
Yes.
no reason even to me. But second, Mina publication was not, let us say, the first one. In this case, no reason to mention this name. I think it's because it's simply very strange practice. But second thing about shadows for Reisner-Nordström metric, because it's now started to be Reisner-Nordström metric started to be popular for observers also, because they published article about constraint on Reisner-Nordström metric. But important thing that is, if you increase in charge, so shadow size is shrinking. So in this case, it's remarkable, let us say, degeneracy. If you allow to have for shadows to have some significant charge, in principle, we cannot evaluate even mass of black hole, because we have to, because there are two parameters, charge and mass. So in this case, we have to evaluate mass from other experiments. For instance, for our galactic center from pericenter shift or something like this experiment, because it's very important. But in this case, I like your let us say about let us say importance to measure let us say distance, but also mass is also important if you allow charge, significant charge. Thank you.
I mean, when you then add also the acceleration parameter and the cosmological constant, you basically just a priori, if you don't have anything, you can't also really distinguish between all of these, because all of these are different. I think then also the nut parameter, when you add it, the shadow is still spherically circular. So this would be another parameter. When you add this, you cannot really distinguish. So
okay, it's good, but what about acceleration parameter for the galactic center or M87? I think it's almost zero for us.
Yeah.
I mean, I would expect that it's to be really, really, really small. So
yes, exactly. I'm saying the same thing. And also, let us say, of course, also cosmological constant is important. But if you apply this for this consideration for the galactic center and M87 is also small.
Yeah, sure. I mean, it's I would personally expect that the cosmological constant for the galactic center supersedes, if it is there, the acceleration parameter. That the cosmological constant has still a much stronger influence, and the black hole moves relatively slowly. I mean, the peculiarity is about this alpha is also you have just a linear acceleration along one axis. I would also not really expect that in reality, but rather that it's some not really linear acceleration, but maybe slight acceleration, maybe it's a bit slow down, then also not exactly in one direction, but moving slightly.
Okay, thank you.
Okay, there's a question by Aroldo.
Yes, so I think you mentioned that this geometry has a conical singularity, right?
Yes.
So can you see any imprint of this conical singularity in the shadow or gravitational lensing? So can we infer the existence of a conical singularity from shadow or gravitational lensing?
So basically from the shadow, when you just take the Boyer-Lindquist coordinates, I would say in the end, no. But basically the photon region that is just a sphere, it's just specific for this coordinates. There was also the work of Gary Gibbons and Warnick, I think was Marcus Werner also involved, I'm not sure, who plotted the photon region in a different set of coordinates, and that looked more like a drop. So the intrinsic geometry is not necessarily that of a sphere. But if we use these coordinates, the most striking, and I didn't really mention it because here it shows very small, I plotted here basically on the axis the geodesics which would cross the conical singularity. And what you can see here, it reaches the ends of these parts of the images of second order. And that we have these parts is basically an effect of this conical singularity associated with the deficit angle, and on the other side with the surplus angle.
Yeah, I see. Thank you.
Okay, I see that Valerio is with us. Welcome, Valerio.
Okay, thanks. Sorry, I was busy with examinations before. Anyway, actually, my question was already asked by Alexander, so I will reformulate in a different way. And the problem with the acceleration is that this model is quite idealized. So in the sense that we have an acceleration, a constant acceleration of this black hole. But if we want to apply it to an astrophysical case, for example, a black hole in a binary system, then probably this model could not be applied even in that case, because the acceleration due to the other star can only be modeled if we model both gravitational fields at the same time. So we should solve the Einstein equations with two masses, basically. And then that could provide an interesting framework in which the shadow of the black hole would be modified by the presence of the binary star. But of course, I think nobody has ever considered this case, the investigation of such a case, because of course it would be much more difficult. But I wonder whether in which limit we could apply your study.
To be honest, I'm not completely sure if you can really apply it to black holes in reality at all. This only measurement observations can show. But what I would expect is when we have maybe very weak accelerations and the black hole nearly moves linear. And I didn't explicitly mention this, but like the string and the strut were associated in a work from, I don't remember the name right now. Volker, do you remember the name from?
It's a colleague from Prague. I also don't remember the name at the moment. Yeah.
So he associated the conical singularities with an inflow and outflow of energy momentum along a null. I think it was a null dust. And I think it was also an inflow of gravitational waves and outflow of gravitational waves. So it would be basically a black hole that is accelerated by or radiates away gravitational waves. What I did here, I left both singularities, but you can also transform one of them away, which then would be either a black hole accelerated by a strut, so pushed, or it would be a black hole then just simply somebody pulls it with a string. But I agree this, in particular, the conical singularity on one axis is it looks on the first view quite unphysical.
Thanks.
Okay, thank you, Torben, again for your talk. I see we have a few more minutes. So in the schedule, let's read general discussion. So if anybody wants to start a general discussion, then we could do this now. Or you can now ask a question to somebody, some of the earlier speakers, provided he or she is still present. Alexander wants to say something. Go ahead, please. Alexander, you have raised your hand. We don't hear you. I don't know what's going on with him. Ah, he wants to show something. Okay.
I can't hear him.
Alexander, you are muted. We don't hear you. Let me see if I can unmute him. Alexander, do you hear us?
Yes, it's now.
Ah, okay, very good.
Now it's okay. Because it's just propaganda of a classical book, you know. That is Chandrasekhar book. And Sergio showed almost the same picture. It's only Kerr-Newman, Kerr-metric, you know, not Kerr-Newman, Kerr. But correctly, Sergio cut this negative eta parameter. It's quite correct because it's negative eta parameter corresponds to vertex motion of photons, and they are captured by a black hole. But it's next slide. That is, if you consider this again, critical parameters which separate scatter and capture, in this, there is remarkable observation. All maximum value for these curves are the same, 27. So in this case, it corresponds to, for this picture, for shadow, for let us say Kerr black hole. And remarkable thing again, so because if you, the maximal value of impact parameter in vertical direction is the same again, but position depends on theta on alpha parameter in this notation as 2a. A is the spin. For instance, if spin is half, so in this case it's 1, it's maximum value. But for Schwarzschild case, it's well known. So in this case, it's if assume that in future people could evaluate for shadow from observations for equatorial plane, who knows properly for our galactic center. In this case, immediately we could evaluate spin without measuring of deformation. That is common for Sergio because probably it's I did not formulate my comment clearly. Thank you very much.
Okay. Yes. What you said about the vertical diameter. Yes, I think that's really very important. So in the Kerr space-time, it is given by the value from the Schwarzschild space-time to within order m over rho. F rho is the distance of the observer. So in this order, it's for the vertical diameter, it's the same value as for the Schwarzschild space-time. That's what Singh calculated in '66. Yeah. Yes. By the way, maybe I may mention that a member of our group, Arne Grenzebach, calculated the vertical diameter for an observer at an arbitrary distance from the center. And then, of course, it's different from the Schwarzschild value. But in lowest order, it's correct what you're saying. It's exactly the same as the Schwarzschild value. Okay, anybody else with a comment or a question? Oleg?
Alexander, yeah. I would like to comment your comment. I'm not sure that I fully understood your idea. So, of course, I know your paper, and I know that there is this nice feature that for every spin, you will have a maximum of vertical axis if x equal to 2a, yeah. But I'm not sure how you can extract spin just from this information, because when you look at the sky, okay, you know, you can measure this vertical size, yeah, and you know that this vertical size happens in x equal to 2a, but you don't know where the zero in the sky, you don't know where the origin of coordinates. So how this information allow you to find the spin?
It's a very good question, and that also it's very let us say complicated, because important thing that if we are considering bright structure around black hole, it depends on our specific model about, let us say, accretion flow. It's in principle our knowledge is very poor in this respect, and of course it's in reality probably we could observe only, let us say, beam of, let us say matter and also light. I mean, it's in counter-rotating, just some spot near the brightest region. I mean, it's brightest region, some spot, not, but important thing then from, there are two questions, two significant questions. One is general relativity effect. In this case, generally speaking, almost always you have some dark region. For general relativity predicted the shape of dark region. But in, I mean, structure of bright luminous structures depends on our knowledge about accretion flow. It's practically, it's still, even for event horizon data, in spite of efforts of hundreds of people, there is no, let us say, generally accepted model for accretion flow. So, but it's true, for, let us say, M87, we practically seen this disk, let us say, face on. So that is another case. But in this case, it's, I mean, it's another problem. But for this case, for equatorial plane, as I told you, that is, its maximum value is very hard to evaluate from observations, because it's, I mean, in maximal, for maximal impact parameter, that is, this region will not be the brightest region for shadow, because it's vertical direction. Photons are preferring, photons and particles are preferring to move along equatorial plane. That is the point. In this case, I agree with your comment. It's not very simple to measure it.
Yeah, I mean that. So my, let me say, objection that you said that we can extract spin without this measuring deformation, and my let me say objection is that you, even if you have ideal situation and this critical, you see this critical curve without any problems in the sky, you just, it's not enough just to know this vertical size and position, because you don't know where's the origin in the sky.
Yes. If you are considering accretion flow, you are right. But if you're considering bright screen, but sometimes you have, well, I mean, bright screen behind a black hole. In this case, that is measurable, you know, quantity. And moreover, people in computer simulation, they showed shape of shadow, even for instance, for when people, let us say, for illustration, GR people, when they showed images for binary black holes, for LIGO, of course, size of the shadow are very small, but they clearly showed rotating black holes, and in this case, it's visible, let us say, shape of shadow, because it's ray tracing. If you have screen behind a black hole,
I fully agree.
It's measurable. I mean, because we have to separate two things: general relativity and astrophysical model, which could give us opportunity to measure this shadow. So, but for accretion flow, I agree with you. It's hardly ever possible to measure, I mean, size of shadow in vertical direction. But for screen behind a black hole, it's quite possible. Because again, it's for simulations, people represented this picture. I saw them. That's it.
Okay, thank you.
Okay, maybe before the Zoom room will be closed down, I should make an announcement which might be important for the speakers tomorrow and on Friday. We sent you the message that you can log on 30 minutes in advance, right? And test the screen sharing. Today, this did not work. They opened the room only 10 minutes before the session started. So this happens again tomorrow. I don't know if it happens, but if it happens, don't become nervous if you cannot enter half an hour before the meeting. But even if it's 10 minutes, I think it's today. I think it was enough time for the people to arrange themselves and to test their apparatus. Okay, yeah, it's 5 minutes over time already. Unless somebody wants to raise an important issue, so that we could fill the time until the room will be closed. Otherwise, I would suggest that we stop here. Yeah.
Thank you.
Okay, then I thank all the speakers very much for the nice talks and for being quite disciplined with respect to time. And see you tomorrow for the second part. Bye-bye.
Bye, see you tomorrow.
See you tomorrow.
Bye.